So good morning. Welcome to this Thursday of the Mars Time Conference. I hope you have a good night, that you are all ready for this new set of presentations. And I'm Noé Lebec, I'm a third-year PhD student, and I will be your chair for this next session. And during this session, we will slowly move from the early Mars climate with Edwin Kite presentation to more recent climate during Amazonian. So the first speaker will be Edwin Kite, and he will answer the question if early Mars self-regulated as a desert planet.
Thank you. Good morning, everyone. I'm very happy to be here, and thanks to all my co-authors. So the first wave of international global Mars exploration has equipped us with rich data sets. And today I'll first review some key points from the relatively young, so Hesperian and Amazonian, physical as opposed to mineralogical record. I'll suggest a model to explain these data, and I'll make some suggestions for future exploration. So post 3.5 billion year surface liquid water was patchy and intermittent. So these plots summarize these data. So both the green and the red points correspond to observations of water-worn geologic features. The blue zone is an attempt to match the data. So early on, we have valley networks that extend to high altitude. But later on, the evidence for alluvial fans and deltas is more confined both in altitude and latitude. And so what you see in blue is an attempt to match a grid of gray gas global climate models to the data. So Michael Michener, who's also here, was involved in this project. In addition to the alluvial fans and deltas, we see 5-kilometer high mountains of sedimentary rock. And these are Hesperian and Amazonian in age. Since sedimentary rock formation almost always requires liquid water, the distribution of these sedimentary rocks is a proxy for the availability of at least small amounts of liquid water. When we look closely at this record with the Curiosity rover climbing Mount Sharp Gale Crater, we see that definitive evidence of surface water is locally present. So what you see here is a Paleolake deposit. So shallow water, open water, so annual average temperature above freezing, with the wind causing ripples of a few centimeters wavelength in this shallow lake. And so Claire Mondreau led this study by the MSL team, which was published a few months ago in Science Advances. One of the things that makes this lake deposit spectacular is that it extends for many kilometers around Mount Sharp, and it's very enriched in metals. We still don't understand why. More than 40 weight percent iron oxide, 2 weight percent zinc, 1 weight percent manganese oxide. But this is the exception that proves the rule. Most of the stratigraphy through which MSL has been climbing is consistent with shallow subsurface groundwater as opposed to surface water. And many sedimentary rocks formed less than 3 billion years ago. And intermittency is strongly suggested because we think that the accumulation rate of the sedimentary rocks was sufficiently high that if they'd been deposited continuously over billions of years, they'd be tens of kilometers tall instead of only a few kilometers as we see. And so in this analysis led by An Lee, who's now a graduate student at the University of Washington, An looked at the crater record both of erosion and of original formation age and found that many of the sedimentary rocks post-date 3 billion years ago. And the same is true for the alluvial fans. And so many people have studied this, going back at least as far as Grahn and Wilson 2011. Our contribution was basically to be more conservative in our analysis, but we got the same result. So we looked at craters on the ejecta blankets of the alluvial fan hosting craters rather than on the alluvial fans themselves, and fit a pulse model in which alluvial fans start forming at such and such time and they stop forming at such and such time. And what we found is that many of the alluvial fans formed after 3 billion years ago. So I can't resist for this specialist audience the chance to make a few suggestions for future data model comparison studies. One is, it's important to mask out young terrains, otherwise you'll get the wrong answer. It's a very good idea to use multiple figures of merit when comparing the data to the models. So these are just some possibilities, but the point is to use more than one. I would advocate against assuming true polar wonder. And the reason for this is that we don't know if true polar wonder occurred. And timescale and intermittency constraints can be as powerful as the geographic distribution in ruling out paleoclimate models. So these are just my opinions, but I'd encourage considering these points in future data model comparison studies. But now on to the main point of this talk, which is carbonate formation and as a regulator of past surface liquid water availability. So we have lots of evidence for carbonates on Mars. If we add them up, the known deposits, we don't get hundreds of millibars. We get, optimistically, tens of millibars. That's not enough to provide a very strong greenhouse effect, but it is enough to suppress evaporative cooling by a lot, and thus makes a lot of difference to the surface energy balance, which controls whether or not you can get snowmelt on Mars. This is just a cartoon summary. Most recently, Tutelo et al. In a science paper reported 5 to 11 weight % carbonates in the sedimentary rocks of Gale Crater. This has been observed over a stratigraphic interval of 180 meters so far. Curiosity continues to climb the mountain. Meanwhile, at Perseverance at Jezero has also reported carbonates. So this is Clave et al. 2024. And we have also reports of carbonates in the soil at the Phoenix landing site and locally in rocks at the Spirit landing site. Now, if you look at the total volume of these carbonate-bearing outcrops, the sedimentary rocks are the most important reservoirs simply because of their large volume. So you've got something between 1.5 and 2 million cubic kilometers of sedimentary rocks, which smeared out over the planet is a thicker global equivalent layer than the soil. What I'm going to suggest is that carbonate formation plus chaotic orbital forcing yields self-regulation as a desert planet. So in this study, we start with uniform initial conditions. So about 3.5 billion years ago, we have about 100 millibars of carbon dioxide. We then use this to drive a liquid water availability model. The greenhouse effect is relatively weak, and so we only get seasonal melting, only at optimal orbital conditions, and only in low spots near the equator, so optimum geographic and temporal conditions for liquid water availability. And so that allows a small amount of carbonates to form. So then we update the atmospheric pressure, we update the solar luminosity, we allow for escape to space using the Ramstad 2018 carbon dioxide escape to space measurements, and then we run the liquid water availability model again. Now, I believe Jack Lascar is giving the next talk. So solar system orbits are chaotic, and so Mars's obliquity is chaotic. And so we drive the model with many different orbital forcings. And I'm only going to show you a couple, but there are many more orbital forcings in the paper. So this is typical output from our model. So the black line is the atmospheric pressure. The blue line is the liquid water availability, and the red line is the obliquity. So the red line differs between model instantiations, so these are just different chaotic orbital forcings. So what you can see is that the black line drops in little pulses corresponding to spikes in liquid water availability. And so what's pushing the system back into liquid water availability is rising solar luminosity. So the sun gets brighter by about 30% over the course of the simulation, which is enough to repeatedly nudge Mars towards conditions that allow some liquid water. But this is not a planet with oceans or seas. This is a planet with small amounts of liquid water availability in patchy oases. Also, these blue lines, these are million-year averages. So if you zoom in the model, which resolves individual orbital cycles, you see that these are actually many small blips of liquid water availability. And so the time during which there is any liquid water availability for this run is only 1.27% of the planet's history, so it's very intermittent. And the area of the planet, the space-time area that has liquid water is an even smaller number, 0.01 weight %. So how can this be enough to make a difference to the planet's atmospheric pressure? Basically because when liquid water is available, the carbonate formation rate is relatively high. It's paced by cation availability, so basically fresh rocks, so olivine-rich rocks, pyroxene-rich rocks, are broken down and transported into the liquid water availability zones, release cations, and that can form carbonates. Okay, so that's the basic idea. Now, only shown here is obliquity, but the other orbital parameters matter as well. If you want liquid water to be available, then you also need the eccentricity to be high, and since high obliquity is a necessary condition for liquid water availability, the longitude of perihelion has to be aligned with the equinox in order to provide warm conditions at the equator during the season when Mars is closest to the Sun. So what does this mean in terms of the duration of wet episodes and the duration of dry episodes? So here the blue lines correspond to the duration of wet episodes and the red lines correspond to the duration of dry episodes. This is only considering the last 3.5 billion years. I don't think this is necessarily a good model for the value network era, which predates 3.5 billion years. The three different lines, so you see there are 3 solid blue lines, 3 dashed blue lines, correspond to 3 different orbital forcings. And the point is that the results are not sensitive to the orbital forcing. So the wet episodes are all brief because they all correspond only to optimal orbital conditions. The dry episodes, by contrast, can last a long time. And so this means that even though liquid water is available, this is a big challenge to habitability because any microbes that have endured on the surface from some hypothetical early prolonged warm-wet era have to then survive tens of millions of years of persistent dry conditions. So that would be a severe challenge to life. And I should also say, by the way, that this basic idea that carbonate formation regulates Mars's atmospheric pressure is not new. It was proposed in the 1980s by Kahn. So what we're doing is the new ingredients that we're adding are chaotic orbital forcing and geographic resolution. So the model does resolve individual seasons, individual orbital cycles, and it's also 1 degree per pixel. And so here is the geographic distribution of predicted liquid water availability. So the main message from here is that the latitude and longitude distribution is not that bad, but the model is over-predicting liquid water availability relative to the observed distribution of sedimentary rocks. In the bottom panel, the purple corresponds to the model predicted liquid water availability distribution, and the gold corresponds to the sedimentary rock outcrops. So I think what is happening is that the sedimentary rocks did indeed form over a broader zone, but where they are thin, erosion by wind has removed them, so that only the places where the sedimentary rocks form thick piles persist to the present day. The latitude distribution is pretty good. The longitude distribution is actually anti-correlated in some places with the observed sedimentary rock distribution. And that's caused by the model wanting to put liquid water and therefore sediment buildup in low spots which are lying in between the sedimentary rock distributions that we see. Okay. So this is a picture of the habitability of our own planet. This remains a hypothesis, but we don't have a better guess. What we observe is that our planet has been habitable continuously for 3.5 billion years. And the hypothesis is that this is a balance between carbon dioxide outgassing from volcanoes and metamorphism and carbon dioxide consumption mostly by carbonate formation, with a residence time of carbon dioxide in the atmosphere plus ocean system of a few 100,000 years. In this model, the sun's brightening is secondary, and orbital change is also secondary, although it can produce spectacular results like the formation of glaciers. It is not actually controlling Earth's surface liquid water availability. On Mars, by contrast, we suggest that the pattern is very different. The volcanism is minor, so of course we have lots of young lava on Mars. We look down, half the planet has not many craters, but the volumetric integral and therefore the cumulative outgassing is very small compared to that of the Earth. And so that means that if you want balance between carbon dioxide out and carbon dioxide in, then only a tiny, tiny amount of time average carbonate formation is sufficient to balance things out. And so we think that the planet is buffered to an only marginally habitable state, so only a small amount of time average liquid water, balancing corresponding to a small time integrated carbonate consumption. So in that picture, the solar brightening becomes a key driver of long-term climate change on Mars. And then the liquid water availability is sort of bundled into packages, so pulses in time, by chaotic orbital forcing. So that's the basic hypothesis, but it is, of course, a hypothesis. And I want to talk about limitations of the model and then tests of the model. So the main limitation of the model is that the liquid water availability model is snowmelt, but any model in which liquid water is available mostly at low spots near the equator and mostly when it's warm will produce the same basic result that I've shown. And so I think there's definitely an opening to include groundwater in the model. Another obvious weakness or failing of the model is that it only produces, the amount of liquid water that it predicts is basically too small to make deltas and alluvial fans. And I speculate that the reason for that is that the model is assuming only liquid water production on flat surfaces, whereas if you have slopes tilted towards the sun, then you can get a lot more runoff. And so I think including slope-sourced runoff would be an important next step for this model. Okay, so how can we test this? In the short term, I think the Yardang unit, which Curiosity is driving towards, will be really important and valuable. The reason is that geologic mapping indicates that the Yardang unit is an outlier of a very voluminous and extensive sedimentary rock unit, sometimes called the rhythmite unit. And so its composition will be an important test of the model. So William Rapin hypothesizes that this will be rich in one kind of thing. I hypothesize that this will be rich in carbonate rocks, carbonate minerals. If it's not, then the story that I am telling you today is probably wrong. So extended missions are very important, and I hope that Curiosity makes it to the Yardang unit in 2026. The orbital data still have many things to tell us. And so I'd like to preview some papers that will soon be published, led by Maddie Tanner, who's a postdoc working with me. And so one is to look at the volume versus time of sedimentary rocks, and also the layer thickness versus time of sedimentary rocks. And so we find that sedimentary rock formation persisted late. So this is a further quantification of An Li's study. But the thickness of sedimentary rocks drops early in Mars history. We're not sure why this is, but I think this is an important constraint on our models. In addition, in a separate paper, Maddie looks at embedded impact craters, so basically impact craters that are sort of poking out from the middle of sedimentary rock stacks, and finds that the accumulation rate of sedimentary rocks is about 10 microns per year. There are big error bars here, but these are very conservative, and I think that the true rate was probably close to the median here. And so that implies many tens of millions of years of wet conditions, probably hundreds of millions of years, but spread out over a time span of billions of years. So I think this is, these are important constraints in our models of liquid water availability on post-3.5 billion year Mars. I'm actually going to skip this one, but just say, I guess, as a connection to the next talk by Jacques Lascar, obliquity versus time in principle can be directly retrieved by using the orientation of the long axes of elliptic impact craters. And I think that with machine learning to extract the ellipticities of impact craters automatically from vast mosaics like the Dixon CTX mosaic, we can use this technique to actually directly retrieve the obliquity versus time, which would be a really since obliquity seems to be so important in Mars history, as in Bethany Ellman's talk, this could be useful in thinning out our models of Mars paleoclimate. And so, in conclusion, come to our Friday talks on Mars terraforming research. I think when we think about the future of Mars, there are several possibilities. Humans could visit, but not leave, but not restore habitability. Or humans could restore habitability. And so some ideas for doing that are both, lying on the table outside, and we'll be talking about them tomorrow. The future is bright. The new Mars transport vehicles enable lower cost and more massive payloads. So Starship had a successful flight test, I guess 2 days ago. If Starship continues to work, then each Mars landing will deliver more payload to Mars' surface than all of the payload that humans have delivered to Mars so far. So thinking about the scientific opportunities that are opened up by that, in terms of more massive payloads, in terms of multiple payloads, is exciting. On the European Space Agency side, Lightship will open the door to getting more instruments into Mars orbit, and I think that's very exciting as well. So what does this mean in practice? Well, we can look for deep groundwater, we can have larger aerial vehicles, and with that, I'm seeing some kind of warning next to Francois, so I'll leave up my conclusion slide and happy to take any questions. Thank you.
Thanks a lot, Edwin. Do we have any questions?
Hi, Edwin. Bruce Tchaikovsky, University of Colorado. On your chart that showed the history of pressure, obliquity, availability, that one, I didn't understand the connection you were proposing between obliquity, pressure, and the availability. Comment on that a bit further?
Yeah, so at low obliquity, the water substance is stored at the poles, which are cold, and so there's no melt. At high obliquity, the water substance is stored at low latitudes, and it can melt, but only if a bunch of other conditions are favorable.
What conditions? Because you have a pretty clear, explicit connection on availability of liquid water here.
Yeah, so high obliquity is necessary, but also high eccentricity, and longitude of perihelion has to be close to equinox.
I still find it hard to understand how with a pressure of only 60 millibars or less, liquid water being stable.
There isn't much, and evaporative cooling suppression is more important than the greenhouse gas.
Thank you.
Hey, Edwin, one question on the prediction on carbonate formation through time. You need to process you have to cool. This involves a lot of storage. Did you quantify that? How much is supposed to land in which sedimentary sequence at which? If you have an idea of how much that means, the Siberian or even Amazonian, in terms of carbonate storage that we should find?
Yeah, so we assume that the carbonate concentration found by Curiosity is representative, meaning that in most sedimentary rock accumulations you should find the same carbonate formation amount. However, we did do sensitivity tests with changing the accumulation rate, for example, and changing the carbonate formation amount. And because the negative feedback is so strong, you get roughly the same answer. Now, if you change the carbonate formation, if you change the carbonate concentration too much, then you either overpredict or underpredict the total sedimentary rock volume. And so the planet integrated total sedimentary rock volume multiplied by the Curiosity measured carbonate amount gives you, low tens of millibars. So, somewhere our nominal model is 35 millibars, but it can be, 60 millibars stored in the sedimentary rocks. Was that your question?
Yeah, I would be interested to translate it into carbonate content. That's indeed very carbonate rich if there is not much sediment.
Yeah, so if you have only 1 weight % carbonate in the Yarden unit, then this model is probably wrong. for example.
Adam Valentino, CT Zurich. So yeah, you talk about sedimentary units and erosion, and now the Yardan unit. And so I would like you to go back to the slide that you had before with your model results. The one after, or the one with the map. Yeah, this one. So is this? Do I correctly understand that the implication of your result is that the paleo-sedimentary kind of deposit that is part of Medusa fossae is also extended where the Gale crater is, and that the Gale crater mound unit may be part of the same old sedimentary deposit that was just a remnant of all this sedimentary unit that extended further south from Medusa fossae?
Zimbelman and Scheidt Science 2012 is the starting point for that correlation. In that paper, they propose that the upper unit, which is the light stuff on top of Mount Sharp, is an outlier of the Medusae fossae formation. However, the lower unit that Curiosity is currently exploring is rich in sulfates, which are not observed over the Medusae fossae formation. So half yes, half no.
Yeah, and very interesting also hypothesis with the Yardan unit and carbonates. My hypothesis would be that you'll start seeing much more amorphous materials.
Well, amorphous materials are present at the 50 weight percent level already in the sulfate unit, which itself is an interesting constraint, suggesting that following, is Brian E. Horgan still here? I don't want to overinterpret the amorphous. Like one straightforward interpretation of the extremely high abundance of amorphous material is that these sedimentary rocks were not heated for long in the presence of water and did not see much water after they were deposited.
Yeah, and it could be that it's the iron oxide amorphous component is, very hydrated, for example, in that unit. So you would see more amorphous component in the iron part. So.
Yes, but of course the Curiosity carbonate discovery was exciting and surprising because the carbonates were present at high abundance and yet not seen in criticism orbital spectroscopy. And so the non-detection of aqueous minerals, in particular carbonates in the upper unit, is definitely not evidence against them not being present. We'll have to drill to find out.
Thanks a lot for this interesting discussion. So please, thanks, Edwin Kite again. Are there any more questions? No? Okay. You have one, sorry.
Well, sorry, I think we have time. One more question. It's about when you calculate the availability of liquid water, I think it's not that easy to have liquid water at low pressure. And I was wondering just what you assume for the evaporative cooling, wind, something, and the availability of water. Where do you assume that you have water available at the surface?
Yeah. So evaporative cooling is okay. Well, first of all, solid-state greenhouse is included, but turns out not to be important. Albedo of 0.28 is assumed, which corresponds to a dust content at the percent level. So that's probably the main reason. If the albedo of the snow is 0.4, 0.5, then nothing happens. The thermal inertia is snow as opposed to ice, and so this corresponds to melting of seasonally deposited water substance rather than ice. The fraction of the planet's surface area that is covered by snow is 5%, but changing that to 10% or 2% doesn't change things much. But I think the liquid water availability model overall is less important than the basic idea of you have water available in low spots near the equator when it's warm, and so a groundwater model would be interesting. Considering the water ice cloud greenhouse feedback, I think would be very interesting. This is not a GCM. This is a quasi 1D model. So checking if other liquid water availability models produce the same feedback, I think would be very interesting.
Okay.
Yeah.
Thank you, Edwin. So now we'll move to the next presentation. So we'll slowly move to more recent climate and a presentation about the Amazonian. So Jack Laska will be presenting the recovering of Mars orbital elements beyond the horizon of predictability through the analysis of the Earth sedimentary records.
So, hello. Oh, yes, I need to speak in this thing. I'm not accustomed to fixed tabulation. So, yes, I will speak of something that I would not dream that would be possible. And here are it involves a lot of collaborators, which are here. Some are geologists and some are astronomers. So I will speak about how we think we can retrieve in an explicit way, in a numerical way, the orbit of the Earth in the rocks. And as we get the orbit of the Earth, we get the orbit of Mars. And we can do that as long as we have rocks, sedimentary rocks, of course, that mean for any time beyond the horizon of predictability imposed by chaos. So let me remind you what is eccentricity. But you know what is eccentricity of a planet. The important thing is this formula, very complicated formula, which shows that the variation of temperature between perihelion and aphelion, the relative variation is the eccentricity. That's for a black body that you would put there. And if you take the temperature of Mars, which is 210 K, that's the average temperature, it tells you that the difference is 19 degrees with the present configuration, but it would be 31 degrees with high eccentricity. So you see, without speaking any of obliquity, we already have a big influence of eccentricity. But of course, on the Earth and on Mars, what counts is the mixture of eccentricity and obliquity, and eccentricity is obtained in insolation through the precession, whether you have the summer when you are close to the sun or summer when you are far from the sun. That makes the big change in insolation in high latitude. So that's Milankovitch's theory of climate for the Earth, and it transposed to Mars as well with higher variation. We have big variation in eccentricity and big variation in obliquity with a very strongly chaotic state. And this is how we tried 20 years ago to recover, 25 nearly years ago, to recover the layering of the ice caps by trying to fit the deposition rate, the dust, to the insolation curve on Mars. And this is how then we also elaborate some model trying to explain the evolution of ice on Mars. So, but the important limitation is the fact that the orbit of the planet in the solar system are chaotic, and that was found almost 35 years ago. And they are chaotic with an exponential divergence that tells you that basically you lose 1 digit every 10 million years. And the big implication, also due to the perturbation of the major asteroids, is that you will never be able to get a solution for an orbital solution beyond 60 million years, starting from the present initial condition. And this is not the eccentricity of the Earth, it's a component of the eccentricity of the Earth that is in fact the major component in the eccentricity of Mars. So that will be quite similar to the eccentricity of Mars. It's a 2.4 million year term. And you see various solutions give about the same thing over 50 million years, but after 60 million years, they give nonsense. And this is really the effect of chaos on the orbit. On the obliquity, situation is much stronger because this is a spectrum of the inclination of Mars. And this is a curve where you have the obliquity and the precession frequency. And this curve would be smooth in a regular region. And when it is anything like that, it means that it is strongly chaotic. And you can go basically from here to here in obliquity, you see, from 20 to 60 degrees in a relatively rapid way. So, and this is due to the overlap of resonance of the forcing inclination term. So you have, for Mars, an intrinsic chaotic system. It doesn't depend much, even if the orbit of Mars would be regular, even if you can predict it, still the obliquity of Mars would be chaotic. But it is even enhanced because of the chaotic nature of the orbit. But there would still be chaotic. So this means that it's difficult for the Earth, for the orbit, you can predict up to 60 million years from the present position, but for the obliquity, the prediction is much more difficult. You will be limited. You are very quickly limited to about 10 million years. But I think this rise in the obliquity at 5 million years should be quite robust. This is what, this is why you can have various evolution of the obliquity. So if we can get some information from the crater, as it was said in the previous talk, it's true that that would be a possibility to rule out some of the solution and to try to decipher what is the real evolution of the obliquity of Mars. And this is, in some sense, somewhat what I will tell you for the orbit now. So the problem of the orbit, how do we define, how are we sure that the orbital evolution of the planet is the correct one? We use first a very high precision model, which is made for ephemeris, so it would be the DE ephemeris in the US, or the model we developed, the INPOP planetary ephemeris. And this use all available data from Earth or space, and it has been, it's basically, we made a lot of improvements starting 20 years ago, and each time we added something, like the latest one was the Juno data, the orbiter around Jupiter. And like that, we have a model with high improvement. These are the residual in kilometer. You see the evolution. Now we have residual for all the main planets of a few meters. So this is how we are sure that our model is very good, and we can then propagate it. But sometimes people would say, but how? You know that it's sure, you are sure of a short time, the time of the observation. How can you be sure further in time? And there are even from time to time some science fool in some sense that sends some letter like this one. This is something I got recently, you see, mail in September 2025, in October, and just a few days ago, and it was sent also to François. It was sent to all the planet, basically. And dear Professor Lascar, our research is that in the year 250,000, Mars will collide with Earth. Very important news, you see. Mars will collide with Earth. You do not respond to our mail. You did not respond to our phone call. Why do you try to ignore the Mars orbit drift? Are you going to down in history as an old stubborn man? Or as Lascar, remember, for clinging to silence while the truth was knocking? Or do you have the grace to turn around? Please admit that the world, as we know it, will end soon. So very important information. And I didn't answer. In some sense, I'm answering publicly here. And and I think Francois, who is got this information. So what is it's what he observed that the orbit of Mars is eccentric, basically, and the center is not at the sun. And there is about 29 pages of completely non-understandable thing. But basically what he says he looks to the evolution of the Mars perihelion distance. He looks only over a few, only with the JPL ephemeris, but here it is over 10,000 years. So you see, the perihelion distance is diminishing, and it's diminishing in a strong way. About 15,000 of an AU in 10,000 years. If you make a rapid count, you find that there will be a collision in the Earth in, as he says, 250,000 years. This is true. So, but this is just the beginning here. If you go back, the evolution is not going down in a straight way. It just goes like that. It's a secular evolution of the orbit, and it goes up and down, and will never go to the, never collide with the Earth like that. So, but you need to be able to answer to that. But, and then, what about in a longer range, of a million of years? How can you be sure that the model is still valid? For example, in a more serious way, Kaib and Raymond have looked to possibility of passing star that would disturb the orbital motion of the planet. So you want to know, is the evolution, is the model still valid when you go 100 million years ago? Of course, you can answer beyond the horizon of stability. You can answer in a probabilistic way. But that's not exactly what you want. You want the real solution. You don't want just a probability of passing star, a probability of chaotic evolution. You want the real stuff. So to get the real stuff, we need observation. And this is what I'm going to speak about, is the observation for the Earth. We are looking into it in sediment. So you see, this is sediment that are core. And we have, if you take this sediment and you take the core, you see here that the black spot will align with the extreme value of the insolation. So here you have depth, here you have time, but like that you have make a correspondence between depth and time, because this is computed from celestial mechanics. And this is how geological scale is made in the most recent time, by adjusting the sediment to the orbital motion. And we are quite confident this is how it goes. You have depth, you have time. This is the orbital evolution. So this is the motion of the planet. And you get the correspondence between depth and time by adjusting the peak like that. But of course, when you do that, it's okay if you have an astronomical solution. You can establish a time-depth correspondence for the sediment, and you get a geological scale. But what we want is not that. We want to recover the information of the deposition time, and we want to retrieve the eccentricity from just the sediment without the need of an orbital solution. We want to use it to get an orbital solution. And this is what we did recently, and it's just published. You just take the stratigraphic data, and by a genetical algorithm and statistical method, we get both the time-depth correspondence and the astronomical signal. How this is possible? This is possible. We make basically a small model which look like what a solution, an astronomical solution is. So it's a very simple model, just empirical model. And we will adjust. So here it is an example where we simulate data. So we take just the evolution of eccentricity, tilt, and climatic precession. We add some noise, and we make an evolution, time-depth evolutions, which show a varying sedimentation rate. We add the noise, you get this. So we put half a noise, and then we look whether we can retrieve it. So this is done by the genetic algorithm, which search for the best curve that would fit the sedimentation rate, and then see if the model, the small model, fit well the data. At the end, we recover in a very precise way the varying sedimentation rate, and so we are quite happy. We can do that with varying form of sedimentation rate. We retrieve them, and we have the uncertainty. And if you look to the original data we had, at the end, we get the eccentricity curve, and this is the black curve here, and we get the correspondence between depth and time, and in a very precise way. You see, there is nearly no difference between the recovered value and the true value. And here, again, we got 0.96 correlation coefficient between the real value that we input and the true value. But of course, this is simulated data. Even if we put noise, this is easy. But now what happens if we take real data? So this is real data from the core I was mentioning previously, and we make the same analysis. So this score has been analyzed a lot, so there is already a correspondence between time and depth that has been obtained. This is the red curve, and this is the genetic algorithm recovering by putting more and more nodes, and we know by statistical analysis that this is the one we choose. It's not, we don't choose it because it fits to the red one, to the red curve. This is not something that we input. We just input, we have this statistical analysis, and at the end we get this. We have the time-depth correspondence, and we have the eccentricity curve in black. So the black curve is obtained only from the sedimentary record, without any input, any astronomical input. The red curve, here it is over 10 million years, so we know it perfectly. This is the eccentricity curve, the real eccentricity curve. And you see we have a correlation of 0.82 between the two, and even visually you see that they are very extremely similar. So, and this is for another core, much older. And again, it is recovered by the genetic algorithm. We find something that is quite similar to what was found by very tedious work before. And again, the eccentricity curve here with a 0.9 correlation coefficient. So here we are in about 40 million years. So you see, we recover, again, the black curve is obtained only from the rock, without the input, without any astronomical input, nothing. So I must say that I was completely stunned that we could do that. I would not have dreamed that it would be possible to find in a such quantitative way the orbit of the Earth and thus of all the planets in the solar system. We have the Earth, but it means that we have also Mars. We have also we have all the planets just by looking to the sedimentary rock. So what does it mean? So now this is what we have been working hard, and it is over a time that is known, so we could make comparison. But of course, now what we want to do, of course, is to go beyond 60 million years. And thus, we are right now analyzing sediment that go up to 100 million years, and it will be already quite a challenge to see if we can recover a full history, but it is not then an extrapolated history. It's an history with the use of this geological record as bounded to be able to say that this was the true evolution of the solar system. And already this shows you that over 40 million years, the solar system was actually as it is now, and there has not been any catastrophic event like an intergalactic dragon coming into the solar system. We can say it's not possible, because otherwise we would not have been able to recover this same evolution. And that will be my end of the talk, I think, right in time.
Thank you very much. Are there any questions?
Hi, Eran Vos, NMD. This is really amazing. I was wondering if you could derive from this also if you get rocks from Mars. What was the past obliquity during the chaotic time before 20 million years on Mars?
On Earth, the obliquity will be, it's not like Mars, because on Mars you have this intrinsic chaos. So on the Earth, the obliquity will be, it will be possible to get it as soon as we have the orbit, we can get the obliquity. The only thing for the obliquity, or more precisely for the precession evolution, is the problem of constraining the tidal dissipation. This is an unknown. We know it roughly, and we have done an extremely, I would say, important work recently about the Earth-Moon evolution. We have made the first model that show how the Moon could have evolved from its birth to the present situation. Maybe you know that there was a problem, because if you look, since the Apollo mission, we know the age of the Moon, which is 5.4 billion years. And we know, with the laser ranging, we know very well the present tidal dissipation. But this tidal dissipation, if you integrate back, before our work, you found that you had a hit with the Earth at about 1.5 billion years. Not total disagreement with the age of the Moon. So what we did was to look in a very precise way of the evolution of the tidal dissipation. That's the main problem, the evolution of the tidal dissipation. And there is, in particular, the evolution in the ocean. And you have some resonance in the ocean, which makes the tidal dissipation more important right now and in some period during the Earth-Moon evolution. So just to make it short, so we have, this is the main uncertainty. So we have something in a gross way, we have this evolution over the age of the Earth. But for the precise evolution, if you want to see something very precise, there is still some uncertainty. And here again, we will rely on geological analysis to try to constrain it.
Follow up. Do you think of some observations that could help you tell what was obliquity 40, 30, 50 million years ago in a precise way? Any kind of observations that will help you? On Mars?
For Mars. So for Mars, as I say, for the Earth, you have the uncertainty in the tidal evolution, but no chaos. For Mars, the main problem is the chaos. So for this, I think that any kind of observation, like what was mentioning in the previous talk, if from the analysis of the crater impact, you can recover the obliquity at a given time, it will help to, as what I am doing here, we will try then to find the obliquity evolution that will fit with this. And from what I've seen here, now I believe that anything is possible. You see, this, I must say, I would not have thought that it would be possible to do that. This, for me, is incredible. Because you see, the data you have at the origin is the data you have is this one. Is this. You have mud. You have a that's the only thing you have. You have this, core of mud, and from this only you recover in a precise way the orbital evolution of the Earth. So, and of course, if you core some sediment on Mars, we could do that on Mars. And we are not the time to do it yet, but I want to reanalyze also what we did on the ice cap of Mars. And
Adam Valentina, CTH Zurich. So interesting work. I was thinking, have you considered to constrain the model using some paleo indicators, for example, looking at these sedimentary rock layers and looking at, for example, isotopic signatures, seeing, for example, how carbon varies, and if that correlates with also what you're doing right here?
I don't understand your question. I just don't understand it. Here, you can take, of course, the proxy you are using. Here, the proxy is, I don't remember what it is. You see here, it is, the proxy is just grayscale. It's just the color
of this. Yeah, but what does the chemistry tell you? Composition, what does it tell you?
But you can have also some proxy that would be, for example, some isotopic content, and that would be another proxy. Practically anything that changes with climate will be a possible proxy. Some are better than other ones. It depends on the core. Sometimes it is some aluminum content, titanium content. Sometimes it will be some isotopic ratio. Some isotopic ratio of, you see, you could have some oxygen 18 over oxygen 16 isotopic ratio. It could be anything, any proxy that will change with climate.
I'm trying to be short. So just a question about the assumption about the sedimentation rate. So did you assume that it should be smooth enough? Because I guess you can also have those oscillations in the sedimentation rate. And
yes.
The rated question is the hiatus. Sometimes the sedimentation can stop.
Yeah.
Eroded. So I guess this is something that is also, that must be assumed.
Of course. You see, for sedimentation rate, we search for some relatively smooth thing. We put much less point, in fact, than what geologists used to put. You see the red curve here is the one that was deduced by adjusting peak to peak to the orbital solution, to the insolation. So in this case, basically, for each precession cycle, you have 1 point. And you go from one to the other one in a direct way, so it is not smooth.
So as an assumption, you can just say that you filter the data, the longest period is the sedimentation rate, and the highest period is the one that you retrieve for eccentricity, for instance.
Basically, you see here it will be some, you can think that this would normally be some smooth interpolation of the actual one, but it doesn't mean that R is worse than the other one. The real stuff may not be this one. It's not. And you had another question about the.
Hiatus, you know what?
Hiatus.
So the
yes,
question,
that was.
I think it's related to this question.
That's typical geological question. What about hiatuses? It's like for a mathematician, they would ask, and what happened in the non-commutative case? For a geologist, he says, oh, but you have hiatuses. Hiatus is when you are missing a part. So in our paper, we look to hiatus. We answer to a referee question about that. We did explicitly. So you take the core, in the example, you cut apart, you stick them. You make the analysis. What will the analysis do? It will be constrained by the two parts, and in fact, it will interpolate, and it will recover the hiatus completely, as long as it is not too large. We could, over 1 million year core, we could take off 100,000 years and still recover it.
Jim Head, Brown University. Jacques, as you and I have talked about before, indeed the geological record in terms of the glaciation as a function of obliquity is a really good way that we can go back to about 250 million years. So I'm looking forward to continuing our discussion on that.
Yeah, in fact, right now we are very busy with the Earth trying to get this data analyzed. But of course, I have Mars also in mind, and we will come back very soon to Mars to really do the work.
So thank you again, Jacques Lascar. I think we are all looking forward to see what could be done on Mars. So the next presentation will be given by François Forget, and it's about the challenge of modeling the recent evolution of the Martian environment at other obliquities and orbits.
Good morning. First, mention that we have a little bit of time because the very last talk of the morning has been cancelled, so we can shift a little bit the break. Of course not, Jack, of course not. That means I may use a little bit of like 20 minutes. No. So, following Jacques' talk, of course, I think I wanted to introduce a series of other presentations that will come this week about the idea of exploring the possible climate at other obliquity and with other orbits and Earth-base of perihelion and so on. So I almost don't need to show this image, it's famous that shows that the obliquity varies a lot in the past 10 million years between more than 45 degrees and down to 15 degrees. And according to Jacques' work, in the past, statistically, it could have been almost down to 0 and up to above 60 degrees, possibly. So, of course, the key question is, what does obliquity do to the Martian environment? Can we model it? And that's really the topic of research that is more difficult than even I used to think. Let's start with the low obliquity. The low obliquity, for many years, based on theoretical considerations, simple models, you can find that in pretty old papers, all very good. You can expect things. You can expect that because the mean insolation at the pole depends on the sinus of the obliquity. Typically, it really decreases, so you have very cold poles. You can assume, given what we know on Mars, that the CO2 will condense, you have a drop of pressure, and because the seasonal cycle will be which will be reduced, you have less wind, less water in the system because the poles are colder, and we expect a very simple planet. I could mention recently some key work, for instance, work by Pierre-Simon and Head that modeled the thermal aspect of this, and they found that, assuming no flow for CO2 ice, that CO2 ice will tend to accumulate at the poleward-facing slot, the coldest spot on the planet, and it was very intriguing, not really at the pole, but also around the pole on this place. Another key work, I think, in the past has been the work by Buller et al. About the coevolution of Mars atmosphere and massive CO2 polar cap. This really, I think, is a really excellent paper because it explains why we have a thin CO2 ice layer at the surface. But it's based on, if you look at it, it's based on a simple model that is really tuned. I think it was a good strategy because the goal was to understand what we see at the pole, but it doesn't describe at all what was going on in the past. So I want to emphasize the fact that you still have a lot of challenge to understand what happened. When you want to model that with a full model and really do simulate what's going on, you have to address many questions. First, if you take Mars as it is today and put to low obliquity, it takes some time for Mars to evolve, and because we use climate models, they are slow, and it takes tens of years or more. It's not that much time, but it's a challenge. Another challenge is very simple, is the fact that our results when you talk about CO2 ice condensation, it depends a lot on the CO2 ice albedo. And we don't understand the CO2 ice albedo. We don't understand the range it can take and why it is higher right now at the South Pole compared to the North Pole. Here I show you an old plot. I like this paper. It's like a 100-page paper by Hugh Kiefer. And it shows the Lambert albedo. So Lambert albedo is probably not the true albedo because of the specular and the phase function as function of insolation. And you can see that the CO2 ice albedo range from a little bit more than 2.2 up to 0.8, 0.7 something, and probably the true albedo, the bolometric albedo, must go to 9 or something like that. So it varies by a lot, and we don't understand why. We don't understand why it's higher in the south. Frankly, so what do? We have to explore the range of possible things, and frankly, it's not easy. Then, as suggested by Krivsalki and Ed, we need to account for CO2 ice condensation on slopes, and that's not easy when you have a climate model global scale. You need to account for the fact that CO2 ice flows on slopes, and that's it's actually true not because CO2 ice is much more able to flow than water ice on Mars. Once you remove lots of CO2, then you have a different atmosphere. What happened? It has been suggested that CO2 will convert to CO if it's dry enough. You can check Yangcheng Liu's talk later this week. What happened in the subsurface ice in a dry environment? Maybe it will desiccate a lot. That will impact a lot of things, including the thermal inertia. Thermal inertia will be also affected by the drop in pressure. And all these effects, really, when you look at them, they can have complex consequences. Another aspect that is a problem is that we don't have much observations to constrain that. I can only cite a suggestion that some of these landforms here could be moraine by past C2S glacier, and that's suggested by Krivsalki and Head in 2011. And of course, we have the data, radar data of CO2 ice reservoir at the South Pole. So I could just advertise, I see the time is really going fast, some work that has been conducted, not yet published, about modeling this past environment. For that, this is work made during Lucas Lunch PhD thesis. For this purpose, we added a parameterization of the local climate and thermal environment on slopes. I won't have to detail that at all. And in the end, you could simulate things like that. What you see here is a representation of what is found by the model globally and looking at the slopes. And the first thing that you see is that what is predicted if you go at 15 degrees obliquity is a massive CO2 ice around the North Pole. That's not what we expect. We expect ice at the South Pole. And the reason is certainly because we assume a constant albedo, the same albedo in the south and the north, and this emphasizes again the challenge about this problem of the albedo. When we do that, we find the pressure drops. It drops by a factor of 2. This is the seasonal evolution of the pressure based on Lucas' work. When you go to 15 degrees, so in the past million years, it's not that spectacular, probably doesn't change that much. What is more spectacular, if you imagine you go to lower value, like 5 degrees, which was sometime in the past, probably, according to Jacques, we don't know. And then, really, the pressure drops to such a level that CO2 becomes a minor species. And you have to imagine maybe we have a planet Mars with a dark sky. You can see stars. No, maybe not dust. I don't know. We have to work more to model that. Now I have a few minutes to go now to the problem of high obliquity. Mars, it's an even a worse problem. So again, if you go to theoretical considerations for many years, starting with work like pioneers like Bruce Jakowski and others, we could understand that if you increase the obliquity, well, you have a more intense seasonal cycle, more wind. That also means that probably the CO2 ice reservoir that is at the South Pole sublimes, you have a higher pressure. And on this basis, we can expect a more intense water cycle. This time, we have geological informations. We have observation of ice ages and various glacier features, landforms, that most of us consider are related to high obliquity. I won't have time to detail them, but you remember you have these tropical glaciers, you have all these glacial remnants in the mid-latitudes. This is a pretty old slide. You have indication that not that long ago, I mean in terms of geological time scale, certainly mid-latitudes were covered by hundreds of meters of more ice, certainly. But you have perch craters and stuff like that. And, oops, I'm going the wrong way. And in addition to that, you have a much more recent latitude demountain ice mantle that will be discussed more in the next talk by Joseph Nard. So what we used to do for many years was to take a present-day climate model that was tuned to understand and to simulate what's going on, and change, for instance, one number. It's a source experiment. You take Mars as we know today, we model it relatively well, we change obliquity and see what happens, keeping the same polar cap and so on. What we found quickly and with others is that, of course, if you have an increased obliquity, especially during summer, you warm the northern cap, which is the main source of water for the water cycle today, and that enhances the water cycle. At the top, you see the typical water cycle latitude as a function of season. You see the source in northern summer that is red at the top, that's on present-day Mars, and you do the same at 30, 40 degrees. And what you find in such a model is that, of course, you have much more water vapor, but as long as you don't go to really high obliquity, more than 45 degrees, not much happens. The water vapor still stays and condenses at the North Pole. At the time, we were quite excited. We found interesting results. For instance, when we find that when we go billion, for instance, on the western side of the Jaun volcanoes, and that was super exciting because at the same time, almost in parallel, it's a nice story, Jim Hens and others suggested that these yellow arrows, units here, are the remnants of the actually former glaciers. We did the same, assuming, for instance, that there will be ice at the South Pole. We found ice on the eastern side of Hellas, and so on, and so on. And it was a good finding because there are plenty of glacier remnants there as well. We later found that if you assume that you have, for instance, ice in the tropics, if you go back to low obliquity, exciting finding, the ice doesn't go directly to the North Pole. It tends to accumulate in the mid-latitude, and at the time we were delighted. We thought that we could explain the mid-latitude mantle, and there were a series of papers like that. More about that by Joseph Nard later. Now, I want to emphasize, and I've been saying that for 15 years, so sorry for people who've seen me. These studies were interesting. False experiments. We learned a lot, but they're wrong. And I will quickly explain why. Oops. There are two main reasons. First, the GCM must be adapted to actual high obliquity climate. We have to take into account the fact that you have much wetter climate, you have more clouds, you have to take into the relative effects and so on. We don't know what to do with the dust, and this will be discussed by Thomas Pierron. And we don't know what to do with the dust because we don't understand the dust cycle today. So what will happen at higher obliquity, that's a real question. Meanwhile, I can give you a flavor of the work we've been doing with high obliquity climate, improving the GCM. What we find is that if you take the same model than before, but this time you take into account many things, relative effect of clouds, you have to improve the microphysics for that because it's really active and the model becomes unstable otherwise. We can take into account surface latent heat effects. For some, it's negligible. The relative effect of clouds is almost negligible today. It has an effect, but not significant. We have to improve the albedo for fresh snow and so on. And with that, we realized that the climate was not at all what we found without improving the model. Very quickly, you have much more water vapor, more clouds, and key findings were these clouds, which they can have a significant warming greenhouse effect. And that's really changed the story. This is an example for the source experiment of taking Mars today, but with this improved model and increasing the obliquity. And what you find is that you can have, at 30 degrees, not that long ago, a mean warming by 1023 K. If you go to 35, the mean warming is 31 K because of the greenhouse effect of water clouds. And I have to emphasize the fact that it's super model dependent. It's a challenge. If you go to higher obliquity, well, I wanted to illustrate the fact that it's starting to be even more difficult because for numerical reasons, and not only in our team, in many other teams, like at NASA Ames, they have tried to work on that for many years, but they have never really published because So the model, the climate becomes quite complex, unstable, and with a strong feedback between clouds, water vapor, and clouds. And I still put question marks, but we are making progress. I hope we will have nice results soon. So that's for the climate. The other point I want to emphasize is that when you want to model past climate, you cannot assume, just prescribe the water ice reservoir. The reason is that ice reservoir tends to accumulate, to stabilize where it's cold, in the cold traps. And if you prescribe water ice somewhere else, then you can have a very unrealistic climate, because you put a lot of water vapor. Okay, it's interesting, you have clouds, but the reservoir sublimes like hair. For two reasons. First, of course, because they must locate, they usually stabilize where it's colder. And the second reason is that when you take an ice reservoir that is out of equilibrium, that must happen in the history, it tends to sublime but then get buried by a lag deposit. That's what we observe in many, many locations on Mars today. Lots of water ice buried, stabilized thermally by a lag deposits. And that really limits the consequence of the water cycle. So to study this second aspect, and this will be described later today, we have been developing a dream model for us. We call that the planetary evolution model, to model the planet in equilibrium, where the water ice stabilizes where it is stable, not where it will sublime like hell. And second, once we have such a model, based on the asynchronous coupling between glacier models and the GCM, we can explore the geological activity that will come to the slow evolution of the orbit, of the obliquity. And I won't have time to describe it. This will be described by Jean-Baptiste Clément later. But this will be a dream model, because with such a model, I've been advertising it for years, sorry about that, we're making slow progress, we'll be able to really, I think, explore the evolution of Mars through time. The ice will move, accumulate, get buried, make layers, and our goal one day, for instance, will be to do a full 3D model and reconstruct the northern polar layer deposits. Why not? But you need all this big machine to do that. You can do it with 1D model principle. Actually, we will present things, but it won't represent the reality. So you can do a lot of toy model and really explore and do good science, but our ambition is to try to bracket the reality and all what could going on. So I will finish my last slide, the conclusion, just repeating that to really address this problem, we need to better understand the present-day climate system. We need to develop improved climate models that can really handle the new environments, and we need something to understand the slow evolution of the glaciers, CO2 and water ice glacier. Thank you.
Thanks a lot, François, for this nice overview of all the hard work that has been done on modeling Mars climate recently. So, are there any questions? Yeah, sure.
Jim Head, Brown University. Thanks, Francois. This is great progress, and we're lurching towards reality here. I just was curious. The tropical mountain glaciers are a good geological observations, and we know the date, and they're tropical. So, is there another way that it's emerging that those can happen without high obliquity?
For the tropical glaciers, no, you need high obliquity. But I think this is not a challenge, because according to your work, they are relatively old. The number I came to my mind is about 20 million years old, and we had time to go to high obliquity and stabilize it. We still, even with the improved model, I think we could explain why it's really there is a strong the physical process that put them here is pretty strong. It's not that monotonous. I hope it will work. It's consistent. What has been inconsistent with the previous model, and more in the next talk, is the latitude dependent model, which is much more recent, and that was very challenging to explain with our traditional view of the past climate.
Yep. Thank you.
Hi, Francois. Bruce Tchaikovsky, University of Colorado. I think what you're doing is incredibly important in order to understand the processes and how they operate. I just want to remind you that there's a parallel approach that is just as valid, and that is sort of a heuristic approach to understanding what happens. For example, we know that as the obliquity increases, we should expect the sublimation of water from the cap to be greater. At high values of obliquity, we expect that water ice would be more stable in the equatorial regions and mid-latitudes than at the poles. So as important as what you're doing is, I don't think we should lose sight of the fact that we have some sense of how the system is going to behave at different obliquities throughout time.
Yeah, I think I completely agree, and I think that was in some way my first slide when I said theoretical considerations, and I even mentioned your name. It's really, indeed, they are make things. But the reality is that when we try to fully model that, and we find that there are processes that we had to neglect with a simple point of view, the effect of clouds, the effect that are in the end looking much stronger than expected, and I think it's quite exciting. We're talking about a planet that was really very different than today. But I agree, of course. But that was kind of a conclusion. We can explore the range of possible changes with simple models, more complex model, or full model, like we ambition to do.
And let me add one point that we have this intuitive sense of how the system behaves because people have developed simpler models in the past, and we take these and incorporate them into our thinking. And now you're developing more complex models that are going to drive the next round of intuitive thinking. So it's a bootstrapping where each approach builds on the previous ones and the others.
Of course.
So Bethany Ellman, also University of Colorado. So just, I guess I have two questions. The first is, and maybe it goes a little bit to what Bruce said. You said something to the effect of, oh, well, we've done this, but those models are wrong. Is it that they're wrong, or that we just don't understand the earlier models of how Mars, present-day Mars, would sort of respond to obliquity change? That it's a matter of the details. Can you maybe say a little bit? First question is, can you maybe say a little bit more about what you mean when you say they're wrong? Because to a large extent, they seem to agree with the geology, and they seem to be largely right. So how are they wrong? And two is, are there new data that are needed, either from laboratory experiment or from Mars, to help inform some of the efforts? Okay, time flies, so I will try to reply quickly. The point is that the work what we advertised in the past more than 10 years ago was really a first experiment. Mars today, we increase the obliquity, we neglect in particular the effect of water ice clouds. Now, and we assume that ice is always below the North Pole, for instance. I think both these assumptions are wrong. So what you find, for instance, is that the climate is much warmer, the ice accumulation is completely different, and I think the improved model, I cannot be faster to say that the improved model shows a high obliquity Mars, for instance, completely different than what is in the earlier model. Completely different. And I think this will be, I won't take more time, this will be developed a little bit by my co-authors later this week. So they are wrong. I don't think they represent the reality, except of course they are good indicators of strong physical process. An example again is the accumulation of ice on the western side of volcanoes. That's a good process. But the latitude departed mantle, for instance, I think is not deposited at all as I suggested. Although this process of going back and forth plays a role, we have to re-explore that. That's it. And with regard to observations, right now, what I'm really dream of is having more information about the actual ages of, it's difficult to do, of the different landforms related to ice accumulation. If we know better the ages of their formation, of their degradation, and so on, that will be a very nice constraint to understand better that. But that's really, the ages are key.
So one last very quick question, as we are running a bit out of time. Yeah. So.
Nice talk. I'm Yi Zhuang from IAP, and just maybe a quick question for clarification. Is one for the modeling of the high obliquity. Are you still assuming that there is permanent water ice cap for the North Polar cap? Or
in what I've shown, yes, but of course we want to improve the representation of the evolution of the ice cap and the formation of deposits and so on. That will be discussed a little today.
And a follow-up question is that I'm wondering if you, I'm not very sure if you are modeling to obtain equilibrium state, but I'm wondering if there is equilibrium state for high or low obliquity. Will this state depends on the initial kind of condition of the places of the water ice cap, or maybe CO2 ice cap also?
We hope to avoid that. We hope to have a model able to, assuming completely different, for instance, water ice distribution, will converge to a situation where the ice will be at a good place based on at least the one that they interact with the atmosphere based on stability. But of course, the layering, the history will be affected, but we hope not to be too dependent. If we are, it's because there is a true physical hysteresis. That may be possible, especially for the CO2 ice, in my opinion. But that's a good question, and we're exploring that. Okay.
Thank you very much.
Thank you. So please thanks François again. And the last presentation before the coffee break will be given by Joseph Nar. And it will be about modeling the very recent ice ages on Mars with the planetary climate model.
Hello everyone, good to be here. So I'm glad that I prepared some technical slides in a way that will maybe answer some of the questions that were asked to François. And so I will manage my time by, I think, skipping my first slides. So this is the stuff that I've been conducting during my PhD here at LMD and continuing a bit in Latmos also, regarding the modeling of the very recent ice ages. So, as François was saying, there's different geological icy landscapes on Mars, and I'm referring specifically to the latitude-dependent mantle, which has been mentioned several times. And so the specificity of this young latitude-dependent mantle, which is inferred, like its age is inferred from geological studies, like global and more localized, is that it's thought to be so aerially deposited, which like results from climate processes, obviously, and those climate processes are obliquity driven. So as we are discussing since the beginning of the morning, and so the principle is that, of course, when you have high obliquity on the northern polar cap, ice is unstable and is thought to be more stable in the lower latitudes. We skip on this. And so, returning to the 2006 paper, where tropical glaciers are formed by increasing the obliquity of the present-day Mars to 45 degrees obliquity. So this was the starting point of a continuous study by a former PhD student at LMD, so Jean-Baptiste Madeleine, who proposed a complex scenario of the emplacement of the latitude-dependent mantle during the very recent ice ages inferred from the geology, which consists of remobilizing the tropical ice deposits that were formed like more than 10 million years ago, and remobilized in the very recent past, so that the ice can flow from the tropics and be stable for a short period of time in the mid-latitudes before, since obliquity was low, going back to the northern polar region. And so, as François was saying, we know that this is pretty much all wrong because of the effect of the radiatively active clouds. So this was overlooked in the versions of the model before the year 2014 or 2012, because it's not really needed to explain anything in the Martian climate in the present day, other than in the aphelion cloud belt, when you have a very, like the thickest clouds you find on Mars, and there are some temperature features that you would need the radiatively active clouds to explain. So here is a snapshot of the modification of the thermal structure of the atmosphere in this specific region and time. And other than this, the radiatively active clouds are not really making anything in I mean, it's a second order process in the present day climate. And so what's complicated at higher obliquity is that when you have radiatively active clouds, you also modify I mean, by modifying the thermal structure of the atmosphere, you also, of course, affect the dust cycle, which is coupled to the water cycle. And you have this kind of intrinsic feedback and coupling, which makes it very hard to model. So here you have the present day water cycle on Mars. The observation is on the left with the water vapor column in the upper panel and the water ice clouds opacity in the lower panels. And here on the right, you have an experiment modifying the microphysics of the clouds, a parameter that I won't go into the details. And you see that a small modification in this parameter, this is quite a bit modification, but it's an n-member experiments. You see that it drives the entirety of the water cycle, clouds and water. And specifically here, if I get you see that in this region, which corresponds to the northern sublimation season, L sub S 90, what drives actually I mean, the entirety of the global water cycle is linked to the sublimation during this season, which is in turn coupled with the radiatively active clouds over the cap, the northern polar cap. And it drives the entire atmospheric water content for the rest of the year. So that's what makes it so complex, is that you need to find the right amount of clouds to warm up the surface, to have some water in your Martian atmosphere, but not too much as to have a very, very humid water, much more humid than the observations. But Jean-Baptiste Madeleine, who implemented the radiatively active clouds in the PCM, conducted some preliminary simulations using the radiatively active clouds in 2014. So this is from his paper, where you can compare the effect, the atmosphere circulation and the atmospheric water vapor content with and without radiatively active clouds. And you see that when you have the clouds, you have an atmosphere 10 times more humid than previously expected in the northern sublimation event. And also the winds are much more intense. It is represented by the red arrow. And so you have that's what François was referring to when talking about climate very different. And this has strong implications for the deposition of the latitude-dependent mantle, because when the atmosphere is so humid, you actually have snowfall and aerial deposition of ice in the mid-latitudes. Like here, you can see the snowfall accumulation rates, which drives the buildup of the latitude-dependent mantle at this time. But these experiments needed so you have a lot of snowfall accumulating in the winter, but it all sublimates in the summer because the pressure is low, and also the radiatively active clouds warm up the surface quite a bit. So the caveat of this study was also to explain the preservation of mid-latitude seasonal ice perennially. And so the actual problem of these simulations, they were quite, I mean, I won't say shady, but unfinished, is that you have, in this particular moment when you have the northern sublimation event, here, at high obliquity, the previous state of the model was extremely unstable. It still is sometimes, but that's basically what drives the high instability of the model with in the scheme of the cloud microphysics, which is extremely hard to model because we don't, it's for numerical reasons and also for physical reasons. The coupling of all these processes has to be done on the dedicated subtime step, which is hard to implement. So that's a lot of the time I spent during my PhD. And here is an illustration. I tried to find some physical parameterization to get a parametrization of this microphysics subtime steps against general cloud microphysics variables like the size of the ice crystals and stuff, anything that I could get my hands on, but I didn't manage to find physical parameterization. So in the end, I settled, and we settled for kind of an empirical parameterization, maximizing the number of subtime steps in a grid cell with the overview of what would be the phase change in this cell, in order to try and get really the optimized coupling of cloud macrophysics with the rest of the climate system. And so, as François was mentioning, the water cycle is also very different at high obliquity, not only in the clouds, but also because the water frost, for example, is very thick, so you have a thermal inertia feedback that was already implemented in the model back in 2009. We didn't have any latent heat of sublimation for the groundwater, so just like for radiatively active clouds in the present day climate, it's really negligible, but at high obliquity, when you have a strong insolation on the cap, it has a tremendous effect. We also implemented some albedo parameterization to try and smooth and get a finer sublimation season, as it is the most important time of the year when modeling the global water cycle. And the bottom left figure is some implementation in the cloud macrophysics itself to make it more realistic. And so with the cloud microphysics subtime step, which is very tuned for the high obliquity climate, and all this change to waterized physics, we get some global water cycle that François already mentioned. So this is a slightly different simulation with different parameters for albedo and thermal inertia feedback and stuff. Well, you see that what's answering Bethany's question is that compared to what Jean-Baptiste had in these preliminary simulations in 2014, you have like a water cycle approximately 5 times less intense than expected because of the latent heat of water vapor sublimation and all the implementations, the more realistic, the more physical parametrization on global, on ground ice physics and on the global water cycle. And so regarding the preservation of the deposited mid-latitude ice during the summer, so the color bars are wrong. I think the bottom color bar is only for the upper panel, and I'm pretty sure the 2 bottom panels are in a different color bar, so just look at the patterns. So here for this specific simulation at 35 degrees obliquity, without making any assumptions for the dust cycle, which is completely overlooked in this work, it has to be reconnected with Thomas Piron works, but without involving any ad hoc parameterization, just the albedo of the frost and the thermal inertia feedback, we get some preservation, like perennial year-by-year growth of mid-latitude ice at a rate of several millimeters per year. Yeah, so this is extremely shocking because I mean, not shocking. It's super nice to find this because the atmosphere is much less wet, is much drier, but nevertheless you have a sufficiently thick frost mantle depositing on the mid-latitudes to be preserved with all these ice parameterizations throughout the summer. And as François was mentioning, this also happens at 30 degrees obliquity, which is completely which was unthinkable for us because we had so much trouble running these simulations and investigating them even at 35 degrees obliquity. It's actually a bit more easy at 30 degrees obliquity since the climate system is much drier also. But still you have a preservation of ice outside of the polar region on both hemispheres, which corresponds approximately to the latest I mean, the lower bound of age of the latitude-dependent mantle inferred from the geology. So this is very, I mean, it has also some caveats regarding the plausibility and the physical reality, but it shows, in principle, that the water ice by itself in this climate, when deposited on the mid-latitudes, can be perennially preserved throughout the years without invoking some feedbacks with the dust lag, the dust layering, or the atmospheric or CO2 cycle or anything. So by itself, it's a really nice result for climate modelers. And so what I want to finish on, my presentation on is this slide. It's a bit, I think only climate modelers were wondering why the latitude-dependent model was so hard to form. And maybe some other communities were already doing their work, assuming that this was what we found during these years. I mean, they had the intuition of it and they believed it. But now, as climate modelers, we have proved it and modeled it. So we are very happy with these results and waiting for the coupling with the planetary evolution model and the cycle. Thank you.
Thanks a lot, Joseph. So here are some questions.
Yes, thank you for your talk. I will go back to the slide you didn't show.
Okay.
The second one. Yes, I would like to know what is the status of my assumption in 2002 now. What is it? Was it completely false? Was it?
You mean like that you have...
That the deposition of the ice cap or the northern ice cap is made with this time scale.
So I feel like the number I have in mind is more like 5 million years for atmospheric physical reasons. But are you just referring to the time scale or to the...
To the time scale, yes, to this curve.
To the bottom, yeah, so what is your question? Is that is the time scale longer than this in the deposits?
Yeah, or no? It's right, is it false? What is the status of this result now?
I actually don't know. I feel like my reference paper was yours because it was excellent. So I wouldn't know. No one has taken its place in my mind.
Okay, thanks.
Mine's an easier. Jim Head, Brown University. First, I want to say that this is exactly what Francois Forget and Bob Heberle and we talked about over 20 years ago is like, okay, we have geological observations, we have climate models, and we're going to iterate back and forth to improve. So this is absolutely great work, okay? But I would caution you that the latitude-dependent mantle is not the same, the 2003 paper is not the same as the Madeleine et al. Paper. It has nothing to do with each other, okay? They may both need to be improved, no question, and I'm anxious to talk about that, but the latitude-dependent mantle is the last few 100,000 years to a million years. The Madeleine et al. Paper dealt with significant thicknesses of ice that are, in fact, much older, have nothing to do with going back and forth. So I just caution you that that's not a good model to use. That was tuned to fit the thick accumulation of ice in the mid-latitudes that's geologically very confirmed to be there, to have been there, not when obliquity at short oscillations, at, let's see, high amplitude, low wavelength, happened in the most recent period, okay? So they're two different things, so I would caution you against putting them together to cast doubt on the Madeleine et al. Paper. Yeah.
Thank you.
Great work, and we're lurching towards reality here.
Thank you.
Really nice work, and thank you for putting this together. I have one comment on your and Francois' talks and the related work, and that is the uncertainties in the behavior of the polar ice that translate into uncertainties in how the system responds under other conditions. At the North Pole, for example, we don't know whether the summertime pulse of water into the atmosphere comes primarily from the white stuff or from the dark lanes. The dark lanes cover only a couple of % of the surface, but they're much warmer. If there's ice at the surface, they can easily supply that entire pulse. At the South Pole, we don't understand the interannual variability of CO2 covering and behavior of an underlying water ice cap. That's exemplified by the behavior observed in 1969 where there was more water observed in the atmosphere using Earth-based telescopic observations during southern summer than had ever been seen or has ever been seen since. And that factor of half a dozen variation in the summertime water pulse from the south translates into a large uncertainty in what's going on at the surface. And both of these, the north and the south, really have a big effect on how you would extrapolate to other obliquities.
That's very true. If I go back to this slide where I showed the high obliquity water cycle, and so I emphasize that the northern sublimation event is the most important to derive the global water cycle. And here you see that in this region where the perihelion is synchronized with the sublimation event, something, I mean, the gap that we observed and that we were happy to get with the improved microphysics is still here. So we actually don't know if this is physical or not. I feel like the GCM that we have is not really the good model to really explore as of its state now. It's too coarse, and the polar regions are not too well resolved. So that this has to be done with, I think, some dedicated study, and maybe not the GCMs. I don't know. It's too broad. The grid cells are too large to do this.
And again, I really like the approach because these models really help us understand what's going on. In response to Bethany's comment earlier, all models are certainly wrong, but some of them can help us understand what the system is doing.
Thank you.
So I think it is more than time for the coffee break. So let's thanks again all of our speakers. And the session will start again at 11:15.
Okay. Okay, welcome back everyone from the coffee break. Even though we have a presentation cancelled, we're gonna keep on schedule so we have enough time for lunch. My name is Lonneke Roelofs. I'm from Utrecht University, where we are with a small planetary surface processes team, but a very nice team. And I'm happy to be chairing this session and to introduce our first speaker, Anna Grau-Galovre. Floor is yours.
Thanks, Anneke. Hi, it's me again. But this time I'm not going to be talking about upflow tunnels. I'm going to be talking about something far more recent, which is the North Polar Layer deposit. Yes, sir. So I'm going to be talking about the NPLD. And instead of talking about the mass balance, which is what we've been discussing a little bit in this session so far, I'm going to be talking about the dynamics. So a little bit of introduction first. The North Polar Layer deposit it's an ice deposit. It consists of about 95% of pure water ice, 5% lithics, mostly dust. It's about 3,000 meters thick, 1,000 kilometers wide deposit. And it's now believed to be around 10 million years old after finding a major unconformity within the deposit itself. So this is the radar data that we have from the NPLD. And actually something that may not strike as extremely unusual to climate models, but somebody that does glacial dynamics will look at it and be like, huh, this is weird, is that the layers that we see in the radar are mostly flat. And mostly flat. That means that in 10 million years, this thing has not deformed substantially, which actually, it's really hard to explain if we run ice sheet flow models on the NPLD as we are used to doing with terrestrial ice sheets. So the key question here and the key word here is that I'd like to bring out the attention that if you haven't followed so far the talks, the NPLD is stratified. And you have these layers that are essentially nearly horizontal with varying amounts of dust and ice in the layers depending on the mass balance and the preservation history of each of the layers. Okay, and as I said before, like something that's striking is actually like the layers are horizontal. The layers are horizontal, and also like high-rise and like high-resolution image data shows no evidence for deformation at the cliffs, which are like essentially like 70-degree slope, pretty much vertical cliffs that are located in this sort of like trough pattern that we see here. So if you actually look at the troughs here, even there, which is like an almost vertical wall of ice, the ice has not deformed. So what is going on, right? Usually ice deposits on Earth and also on Mars deform viscoplastically under their own weight. The deformation velocity is parabolic. It means that it's maximum at the surface and it's zero at the base as long as the deposit is cold base and there's no water at the base, which is the case of the NPLD. And that means that deformation should be maximum near the base, but we don't see that in the radar. Here's an example of what deformation structures in ice sheets on Earth look like. And you can see on the left side, that's a radar image from the Greenland ice sheet, and you can see these massive, like hundreds of meters, big rolls that are formed like near the base of the ice cap. And near the margin there, you can really see like very clearly the deformation. But actually, if we look at the stratigraphy of the NPLD, this is what we see. We don't see much of this sort of like major, like large-scale structures. That's very different in the SPLD, but I'm not going to touch that with a stick. The NPLD is pretty much just horizontal layers. So then, you know, like looking at the observations, to fall within the radar observations, the base of the NPLD must deform slower than 100 meters over 10 million years, which is the lifetime of the NPLD. To fall under high-rise observations, the surface of the NPLD must be deforming slower than 50 centimeters over 10 million years, because we don't see observations of deformation. However, to date, the flow modeling efforts have broadly over-predicted the velocity of the NPLD deformation, and essentially like the predictions from models show that, well, we should actually see something. And the problem with these models is that they've essentially treated the NPLD as a bulk mix of ice and dust. Essentially, you have like a 3 kilometer or like a 2.5 kilometer thick glacial deposit with some dust mixed in, and then you just run like normal terrestrial ice sheet models. But that has failed to reproduce observations. So the question here is like, okay, so actually like let's not ignore stratigraphy, let's try to understand, you know, what the behavior of these different layers with different dust contents is doing, controlling the dynamics of its internal deformation. So this is what we're going to be doing here. And the idea is to develop a model for stratified ice flow dynamics with realistic NPLD-like stratigraphies, and implement realistic rheologies of ice and dust mixtures, including the exploration of possible rigid layers that are jammed inside of the NPLD. And then essentially what we're going to do, me and Isaac, we did a Monte Carlo exploration looking at different possible dust contents. We don't know, we cannot constrain exactly layer thickness and dust content, particularly as we move to the bottom of the NPLD. So essentially we did a random exploration. And ultimately, we're looking at possible fracture mechanics. So what are these rigid layers that would be these lac layers that we've been discussing before in the NPLD? Do they break, or what happens with them? So this, you know, like it's taking a step back from like typical complex like 3D ice sheet models, and actually like focusing a lot on what's going on in terms of the rheology. And the rheology, the behavior of ice dust mixtures is complicated. And I will say now, there's work that needs to be done in this direction. But anyways, we'll start with the easy part, the part that we know more or less well, which are the pure ice layers. So some of the layers in the NPLD are believed to be like very near 0% dust. And for those, it's easy. So we have, these are the equations, essentially. Driving stress is driving force. The response to the driving force is the Niglen law of ice flow. This is the typical like flow relationship for ice. You apply some pressure on it, and it deforms accordingly. And it will deform, so what you see, the softness parameter, the A parameter there, it's very sensitive on temperature. And, you know, like we're going to be running like cold and warm NPLD scenarios, because as we play with the obliquity, we are changing the temperature of the ice sheet also. So now we are starting to add dust, and things become a bit more complicated, as dust essentially will make ice grain crystals a bit bigger, which has a stiffening effect. So as we move upwards into dust content, we're going to have stiffer and stiffer layers, which actually require a bit more stress to start deforming. So the softness parameter now changes, and it has this essentially like stress enhancement factor, which depends on the dust content. The more dust, the stiffer. But that's true up to 67%. At 67% of dust, we have this funny jamming behavior. So I'm showing here a couple of papers showing that actually as we move closer to the 67%, you can see, for example, like at the bottom left plot with strain and time, strain becomes constant with respect to time. That means that this is no longer deforming, right? So this would mean that we have these sort of like possibly rigid layers in the structure of the NPLD. So we're taking those into account. So what we did is like a 1D ice flow model. This is just the Stokes equations, and what is different is essentially like adding this like depth variable viscosity and accounting for rigid flow layers with boundary conditions. Essentially every time that we have a rigid layer, the velocity goes to 0, and a stress is applied on the rigid layer. So to play with dust content and thickness, as I said before, essentially we based ourselves on observations down to the first 500 meters, which are relatively high resolution in terms of layer thickness and dust content. And then we then proceed down to the base of the NPLD with mass balance models by Bitberg and others. As we see, as we move to the bottom of the NPLD, we expect more and more dust content, but in both cases, we actually do expect, and if you look at the dashed line, that's the 67% rigid layer, so we do expect the presence of at least some rigid layers, right? So we took real radograms, and we essentially adapted the density structure from the radiogram, and then we added noise, and this is where the Monte Carlo strip comes in, and the noise essentially is changing the thickness and the dust content of each of those layers. So we use 5 different radiograms as a baseline, and we run more than 150 simulations. We did cold runs, and we did warm runs at 160 Kelvin and 170 Kelvin. So these are the results, and what I want to show here is just notice how different the velocity is at the bottom, the x-axis, how much does it change if you actually do consider the presence of these rigid layers in the NPLD? And look at the order of magnitude. That we're looking at centimeters per million year. Centimeter per million years means that in the long 10 million year long lifetime of the NPLD, we've moved by like a few centimeters, which essentially means that we're not going to see it, which actually is consistent with observations because we don't see it. So what we see in this figure here on the left of either plot is going to be the dust content, the density structure. So the lines that you see crossing that dashed line are rigid layers. And you can see that the rigid layers match places where the velocity in the NPLD goes to 0. And yeah, like the whole behavior of the velocity is going to change depending on the number and the position of rigid layers. So if we look at the flow statistics from Monte Carlo, and like these are several different profiles, so like playing with dust content and viscosities and thickness of the different layers, you can see how much it can change, right? But if you look at the right plot, essentially this is velocity versus dust distribution. And, oh, there we go. So the velocity is in the y-axis, those are meter per million years, and the number of rigid layers is at the bottom. And as you can see, as we increase the number of rigid layers, without changing the total dust content, and we're always staying at 5%, it's just a matter of how is it distributed, we actually go down to rates that are like about 1 millimeter per million, which is essentially nothing, right? So these are the Monte Carlo statistics for the internal velocity and the surface velocity. So then what happens with rigid layers? What you're applying, like the ductile layers are deforming, they're putting stress on the rigid layers. Do they break? Do they hold? We find that 77% of the cases for the cold NPLD run at 160 kelvins, they don't present fracture. So what I'm showing here, this is a typical Moore diagram, right? The red line is the failure envelope, and the blue, that's the Moore sphere, essentially looking at confining and deviatoric stresses. And we can see most cases, actually, we don't necessarily see the fracture of these rigid layers, but however, in some cases we do see them, particularly when there are very few rigid layers, we tend to see more breaking. When rigid layers are near the base, so they hold more deformation, and when the thickness of the ductile layers is big. But now the fun part. The fun part is that we could perhaps be seeing some of these rigid layers. So this is a high-rise observation courtesy of the high-rise team, and particularly Shane. And perhaps what this is showing us is boudinage. So boudinage is the process of fragmentation of rigid, brittle layers that don't have a tendency to deform plastically, and they're sandwiched between ductile layers that do deform plastically. So these are a couple of examples of boudinage in terrestrial environments, and perhaps what we're seeing here is observational evidence for the presence of some of these rigid layers. So, conclusion, the NPLD flow rate is extremely sensitive to its internal stratigraphy. An average order of magnitude deformation rate for the NPLD you can think about is going to be around centimeters per million years, time integrated across warm and cold obliquity excursions. And this is consistent with what we see, both in radar and in high-rise. And the fun part here is that, you know, like a lot of ice deposits on Mars are actually stratified. And this becomes more and more evident as we're like exploring obliquity excursions and thus behavior. And that means that it actually matters to consider what the internal stratigraphy is and what does the dust do and how is it distributed inside of the ice deposits, so we can actually understand how they behave in the long term. Thank you.
Thank you, Anna, for explaining why we don't see something. That's really interesting. Go ahead.
Excellent talk, Anna, as usual. So I just wondered with the boudinage lower layer, could that be a CO2 layer, like occasional CO2 layer? Can you rule that out? It'd be great if you can.
So yeah.
We don't see any deformation on either side of that. So yeah.
No, we don't see much CO2 in the NPLD. And also, like, if it was a CO2 layer, like, then the rigid layer would actually belong to an ice layer. And I would not expect it to deform with this morphology. I mean, this is something we can discuss later if you like. But I would expect if it's a ductile layer that is deforming faster because CO2 is more plastic than ice, and I would expect it to be more uniform than that. Yeah.
Okay, two quick questions in relation to that. So can you, you may have mentioned this, and there's a lot going by very fast, which was great. Can you constrain at all the geothermal gradient? And secondly, the age of the deposits. In other words, you know, the obliquity variations would suggest that significant parts of it may be coming and going with time.
So we could use the lack of deformation and the flow rates. If we believe the model, we could use the fact that there's no observations to put an upper time constraint on the base of the NPLD. We could do that. We haven't thought about that, but that's an easy thing to add. Beyond that, I don't think we can put a minimum constraint. I think all we can do is like an upper order of magnitude. Yeah, thank you.
Very nice work. I just wanted to ask a question about so the viscosity is the key parameter. So how much dust you had to include to stop the flow, so to have such a high viscosity? The second question is, would it be possible to have also an effect of the grain size? Because there's also an effect of the grain size on the viscosity.
Yeah, I mean, sure. So the first question, dust content. So all the dust content, the bulk dust content of all of the runs, it's 5%. So we are not changing the amount of dust, we're just changing how it is distributed. And then the second thing...
Yeah, and on this, but in some layers, it's fragile, so it's not flowing. And so on this particular layer, what is the dust content?
So below 67% is ductile.
Okay.
And we consider grain size growth with respect to like the dust content. Above 67%, following empirical work, we have considered that those are going to behave like rigid layers. Yeah, so that's a difference.
Okay, very good. And about the ice grain size?
I mean, this is still a bit of an unknown, right? Like what the grain size is within the NPLD and what, if it's a 10 million year old ice deposit. I mean, we know in Antarctica that the age of the ice has an effect on the grain size and the distribution. But I don't know. I played with terrestrial models because we don't know anything about what we expect the long-term evolution of grain size to be.
Thank you.
Yeah.
Jim, time for one quick question?
Jim Head, Brown University, just, you know, this component here, boudinage, this really looks like shear is involved. If you look at the lower right-hand one, that looks like vertical compression and boudinage, whereas the one in Connecticut, they definitely have undergone shear. So that's something to think about. Maybe there is some lateral movement there as well. Might factor that into your thinking.
Yeah, I mean, we can chat about that. Yeah, absolutely.
Okay, thank you very much, Anna, and the people that asked question. Then I would like to invite Jean-Baptiste. Next speaker is Jean-Baptiste Clement. The presentation is up. The floor is yours.
So, hello everyone, I am Jean-Baptiste Clement, a research engineer here at LMD, and I'm working mainly on the planetary evolution model, which is a tool that I'm going to describe today. And I'm also want to talk about the first application about the North Polar layered deposits. So, as I'm sure you know, we are using GCM, Global Climate Models, and they are giving quite convincing results. However, they involve many physical processes, and so you need quite tiny time steps to run, and so it prevents their use for simulations billions of tens of years for Mars. And you can also use 1D climate on the other end, but of course this type of simulation, their scopes remains limited because they are using like prescribed fluxes or prescribed initialization, so you cannot infer much things about them. And in all cases, whatever you want, 1D or 3D climate, they are strongly dependent on the fluxes and the reservoir you put initialization. So we want to get rid of that. On the other hand, on Mars today, we can observe many geomorphological features which we think are the results of long-term processes like thousands or even hundreds of thousands of years. So here you can see some terrain which are thought to have been carved by liquid water for early Mars, glaciers, remnants of glaciers, and of course here the NPLD. So that's why we have a need for climate simulations over thousands of years. That's why we want a tool to do that, and that tool, as François Forget described it a bit earlier in a presentation, we want to tackle two objectives. The first one is to model the planet climate in equilibrium, so this tool will allow us to get that, and it's quite important because getting the planet with a climate in equilibrium will allow us to use it in order to make new initialization for other simulations to get the climate evolution. And the second objective is, well, the one that I would be interested in for the NPLD is to model the planet climate evolution according to some external forcing. So also we want to model early Mars, and it was a talk about hydrology done by Alexandre Gauvin yesterday, but here I'm going to focus on the variation of obliquity. So as you sure know now with François Forget and Jacques Lascar, you have a very different planet at high obliquity for Mars and at low obliquity. And so I will explore the full variations of obliquity, eccentricity, and the solar longitude of perihelion. And I would like you to notice that a million years ago, the obliquity of Mars was more about 35 degrees before a shift and going what was for the two last million of years around 25 degrees. So I will not detail the climate conditions at low and high obliquity for Mars because it has been done by François Forget. But to sum up, at low obliquity, you end up with a really dry and with low pressure atmosphere, such that you have ice which condensate at the pole. Whereas at high obliquity, the planet is much more different with pressure increase and high humidity, and you have the cloud effect. Everything has been explained by Joseph Nard just previously. And so what is that tool? The PEM, the Planetary Evolution Model. So the core idea is to make an asynchronous coupling with the PCM. So what we do is that we simulate 2 years with the GCM, and the PM will take these 2 years to compute yearly average quantities and compute tendencies. And with that, he will update the yearly average quantities with his own model year after year. And it will stop until some stopping criteria are met. The stopping criteria are possibly the ice coverage changes or the surface pressure change. And once they are met, the PM is stopping, and it recalls again the PCM, 2 years of GCM simulations, in order to have like a new state of climate and update the average quantities and the tendencies. And then this cycle is repeating again until the duration you want is met. So that's the idea of the PM. And inside the PM, you have many models to update these average quantities, these reservoirs. So the most important one is, of course, to make the ice at the surface sublime and condensate. So we take into account water ice and CO2 ice. But we can also, thanks to a subslope parametrization, make the glaciers flow. We have also the evolution of the subsurface with the ice table dynamics and some schemes for adsorption and desorption. Of course, with all these reservoirs evolving, you have to update also some properties like the surface pressure and the soil temperature. So what we do. One little trick which allows us to make the PM simulate longer is that as the pressure is changing in the PM, we have to adapt the tendency for the ice sublimation condensation, and this adaptation allows us to work longer with the PM. So now I would like to talk about the polar layer deposits, and I will focus on the North Polar Layer deposits. So as Anna told about, mainly you can see that you have an alternation of dust-rich and ice-rich layer, and the main process which is thought to be the driver of this result is this one. So when you have low obliquity conditions, the climate is such that ice is condensing on the surface with dust inside, which contaminates the ice. When the obliquity is rising, then you make climate conditions where the ice is subliming, and when it sublimes, it leaves a dust-like layer behind. And when this dust-like layer is growing, it creates a resistance for the sublimation flux, and this will be described by Eran Vos just after me in the presentation. And when this dust-like layer is thick enough, it prevents the further sublimation and protects the ice underneath. And when the condition for ice to condense at low obliquity are met again, then you create a new layer. For my simulation, I will do like a really idealized case in 1D. I will put myself at 85 degrees north, and I will use very simplified scheme in the PCM to get fast simulation, and I will force the humidity and the water ice clouds in the atmosphere. I will force also the surface pressure. And I will try to simulate the last almost 2.4 millions of years following the full variations of orbital parameters, obliquity, eccentricity, and LS of perihelion. Of course, the model is already can take into account many things, but I will skip them because I want the things to be simple for that case. So here are my results for this really simple ID case. So you can see in the bluish colors, this is the ice. The more the darker it is, the more you have dust. And the curve is the variation of obliquity at the same time. And it is colored in green when the PLD is growing, in red when the PLD is depleting, and in yellow when it's stable. So as you can see, you have many variations of obliquity for the 2.4 millions of years, last 2.4 millions of years. And we end up with 14 dust-like layers with almost 250 meters high PLD. And I must point the fact that it is heavily dependent on the forcing you do, because here, for example, I try to parameterize my humidity, my pressure, and my dust tendency according to the obliquity, and I got like really, the big picture is quite similar, but in detail you can see that I end up with almost just 100 meter high PLD, and the ice has less dust content, which is actually more realistic. Here you have like a focus on one event, so you can see the ice which is growing with different dust content, and when the obliquity is rising, you have sublimation, and little by little the dust-like layer is growing, and it prevents the ice to sublime when you end up with high obliquity. So here it is. As a conclusion, so the PEM is a really new modeling paradigm, and it works together with the PCM, and this allows us to simulate thousands of years, even hundreds of thousands of years. In 1D, you can see we simulated even millions of years. But there are two ideas. First one is to get stable reservoirs at planet scale in order to, for example, to make new initialization for over simulations. And the second one is to simulate the climate variations of the reservoirs, for example, like the NPLD I showed you. And this, I expect, will allow us to explain the geomorphological features. But as I said, for the 1D, everything is really parameterized, and so we need to go to 3D, which are actually working on right now. And we have like many plans for the future of the PEM. Of course, we want now to explore scenarios with high and low obliquity. So also we want to improve, as François said, our PCM to have models which are more able to simulate the paleoclimates. And you heard about the presentation yesterday of Alexandre Grovin about the hydrology, and one of the next steps really soon is to integrate the hydrology model of Alexandre inside the PEM to try to make some early Mars simulation with that. So that's the plan. Here I put all the team working with me on topics related to the PEM or on the PEM, and I think everyone is here at the conference, so please feel free to reach them and chat with them. I'm sure we are really happy to share what we learn about that. Thank you.
Thank you, Jean-Baptiste. Are there any questions? Audience, oh yeah.
Maybe one question, very nice work. I have a question about this dust lag, how increase with time. Actually, when there is a small dust particle on top of ice, usually they are darker, and there is a process that sink the dust into the ice. So I guess you didn't take this into account. So what is the microphysics to accumulate the dust?
Actually, here the dust that you see accumulating is just the dust which was inside the ice, which sublimes. So you compute the sublimation rate of the ice, and you know, based on the dust content of the ice, which is the amount of dust which is remaining. But true, we are looking for more processes to be more detailed. I didn't know about that, but sure, maybe we can try to take into account that. I know that we want also, and it's almost ready, to make also ice grow inside the dust lag layer, thanks to ice pore field ice, with a scheme from Norbert Schorghofer.
And another question, what is the thickness of this deposit here?
For this simulation, where you have actually a lot of dust, the dust thickness, the thickness of the dust-rich layer is almost 1 meter thick.
Jacques Lascar, Paris Observatory. So the dust layer protects the ice underneath, but up to which obliquity? At which obliquity it will still sublimate?
As you can see here, it depends actually, because if you put like a variation of obliquity, but you put constant the LS of perihelion and the eccentricity, it will protect until like I think it's, my memory is like 27 degrees. But here you see that there are many differences. It's because it's modulated by the eccentricity and the LS of perihelion. So it depends actually.
But maximum, but what about 40 degrees?
Here in my simulation, I didn't simulate up to 40 degrees. I think the most is like 35 degrees. But we have to compute that simulation. I know maybe Eran Vos, just after me, will present that.
I have one small question. After a period of stability, the polar deposit starts to grow again, but then I saw in, I think, a next slide, that at first the dust content is quite high and then it decreases.
Yeah, because the way the dust is accumulating right now in the PM is really, really simple. It's just a dust tendency, which is constant in time or parameterized according to obliquity. So if you end up with like a high rate of ice condensing, then the dust content will be really low. But
okay, so that's not per se a natural process. It's
no, because we don't know many things about dust. I think there is also a talk about Thomas Pierron later, talking about dust, and maybe he will give some insights about that.
Okay, thank you very much.
Thank you.
Then we need to move on to our next speaker, Eran Vos. And Eran, before you start, I want to thank you for all your help this conference with multimedia. I think without you, there would have been many more.
Thinking about the switch from science to IT.
Very stable career path.
Thanks. So this is actually a continuous of JB presentation. I'm going to talk about high obliquity exclusion using the planetary evolution model. It's a work we have done in our LMD team in the Mars through time ERC. And the goals of this is basically we want to be able to simulate the orbital-driven ice migration from the poles to the mid and low latitudes as obliquity increase, but also the subsequent return of the poles to the poles as the obliquity decrease. Eventually, we also want to be able to compare the ice distribution and the polar stratigraphy that we get with observation to constrain the range of plausible climate and ice migration scenarios that we get, because it's really we can change a lot in the parameters in the model, and this can have a strong effect. So the motivation of this work is quite simple. As you see, everywhere we look in Mars, we see either ice, subsurface ice, or remnants, glacial remnants of features of ice. We want to be able to understand when this ice, where this ice is going, when, and how does it return to the following the orbital configuration. So over the years, our evolution of how ice migrate due to orbital configuration have changed drastically. In the 1960s to 80s, we understand that the orbital geometry matters and that obliquity and precession change insolation enough, and we can alter stability. This was a work by Leighton and Murray and Ward. Later in the 80s, 90s, and 2000, Bruce Jakowski and colleagues linked Mars orbital changes to the migration and long-term storage of ice and CO2 across the planet using really nice and simple models. In 2003, Jacques Lascar calculated the orbital solution over the last 20 million years, showing a large variation of obliquity between 15 to 45 and eccentricity between 0 and 0.12. And Jim had identified the latitude-dependent mantle, ice-rich deposit in the mid-latitudes. And then we are starting to work a bit with more complex models. So Bruno Levrard used the Mars PCM to show that the latitude-dependent mantle, Francois mentioned it before, was formed through migration from equatorial reservoir during orbital shift from high to low. And Francois showed that he showed this plot many times, that under 45 obliquity, we can create ice in the model where we see glacial features, remnants in the tropical mountains of Tarsis. In 2012 and 2014, Medlen et al. Developed the radiative active cloud scheme and showed that insolation and topography control exactly where snow and ice accumulates, and it's a function of a different orbital configuration, and maybe the latitude-dependent mantle could also be deposited from sublimation from the NPLD. Joseph and Francois upgraded the radiative active cloud, and this is a paper in preparation, and they showed that the LDM was probably deposited at moderate obliquity. This is, you saw this figure many times. And just last year, our team showed using a new subsurface schemes that JB showed before, and I will elaborate, and showed that the latitude-dependent mantle was deposited in the last few million years. So we can run the model in many orbital configuration, and this is what I show here. I show a probability density function of the surface ice accumulation from an ensemble of obliquity between 25 and 45, of course with the active radiative clouds, and we can see that basically ice can be deposited in many locations. It can be deposited on Tarsis, it can be deposited in Elysium, in Utopia Planitia, in Arcadia Planitia, around Hellas, and basically next to iGyre. But basically, we can put ice almost everywhere. It depends on the amount of humidity in the atmosphere and what is the orbital configuration. The atmospheric water content, the humidity itself, is a function of the orbit, but it's a bit neglected that the amount of humidity is actually not only a function of the orbital configuration. If you put obliquity to be 45 and you don't have an ice source, you don't have humidity. You need an ice source. And if this ice source is not at the surface, the amount of humidity you get is much, much lower. I think Michael Mishna has a paper about it and showed it in 2008 or something like this. So I played with the model a little bit, and I put obliquity 45 and LP of 90. This is super extreme, and I show here in blue all of the places ice can be accumulating. This is, of course, an infinite ice reservoir in the North Polar Layer deposit. However, when we don't assume surface ice, stuff changes. In this plot, I show here the accumulation rate of this accumulated ice, but now the NPLD is no longer on the surface. I buried it in 10 centimeters, and suddenly we see that many locations that ice has been accumulated is now sublimating, which tells us that the migration process is complicated. Maybe even in the tropics and in the mid-latitude, we can have layers of ice. At the beginning, some layer was deposited from the NPLD, and later, when the NPLD became buried, new sources, as it was first places where ice accumulated, became source until obliquity changes and so on. I will skip this slide because JB did such a good job showing the planetary evolution model. And I will focus a little bit about the lag layer scheme. So, as JB said, if ice at the beginning we have, you can see, no. Maybe I can change this. Okay, perfect. So, it's also good to be an IT person. So if we have ice, and this ice has been lost to the atmosphere, it creates a lag on top of it. And the real question is, what is this, how this lag behaves? So we implemented a lag layer scheme. So far in the model, we had only frost-atmosphere interaction, but we added the subsurface ice-atmosphere interaction and subsurface ice-frost interaction. The governing equation we got after many manipulations that Francois helped me with is this. So we got the flux, which is a function of the density, the pressure, the drag coefficient, the wind, the amount of humidity in the first layer of the atmosphere, the density of ice, so this is given by the saturation and the saturation vapor of around the ice. So this is given by classical Perron. And it's 1 over 1 plus R. We call this R the resistance. What is this resistance made of? We call it the resistance because it resists the ice from sublimating. So the R is made of Z ice, which is the depth of the ice, divided by the diffusion coefficient, which is a big unknown. It can vary over order of magnitude, the drag coefficient, and the wind again. So if we plot the subsurface ice flux reduction factor, 1 plus 1 over 1 plus R, as a function of Z ice, and we can see how the flux decreases significantly. So it's enough to have about, I don't know, 10 centimeters to decrease the amount of flux by order of magnitude, and about almost 2 meters to decrease it by 2 orders of magnitude. And this is really interesting and surprising. What we show here is the depth of the ice as function of ice loss in latitude 80 for obliquity 35 and LP 90. Quite intense, I would say. So as we put ice on the surface, we have about 140 millimeter per Mars year. At 1 centimeter, we have 250 millimeter per Mars year. 3 centimeters, we are already decreasing to about 40. 5 centimeters, it's about 10. In 7, it's a few millimeters. And at 10 centimeters, it's already completely stable. The first drop from 0 to 1, this is because there's a change of albedo. If you have ice on the surface, the albedo is quite high. And when it's buried, you have a dust. So it's a bit lower, so you can get more warming. But I want to look at it for a second and understand that this drop is huge. So it's enough to have few centimeters to almost completely shuts down the loss rate at obliquity 35 and LP 90. This is remarkable to me. This happens because the lag layer acts both as a diffusion barrier, but also as a thermal insulator. So first, it prevents ice from loss because it needs to diffuse through the pores. But secondly, it removes the maximum temperature around the ice, and therefore the loss rate is, the sublimation rate of the ice is much, much lower. So I did the same trick as JB did. I ran it in 1D just to have some kind of qualitatively result. And this curve is exactly like JB. It's the obliquity. And I'm a bit more traditional person than JB. So I placed only 1% dust in the ice, no matter what happened. As much ice as we have 1% dust. And I put here 3 obliquity cycles, 2.5 obliquity cycles. So at the beginning, ice accumulates as low obliquity. When a certain threshold, we go over a certain threshold, ice becomes to be unstable and losing, and until the lag layer is big enough to protect it, and then it's protected completely, until again the obliquity is low enough so we can accumulate, and again we can create 3 kind of cycles, obliquity cycles. There are 2 differences. There is one really big difference in this plot compared to what JB is, and here I plot time between 8 million years to 6 million years, and my plot goes all the way to 45 obliquity. This really challenged the idea that the NPLD is only 5 million years old, because if we get a thick enough dust layer, we can protect it even at obliquity 45. Of course, this is a matter of how long do we have obliquity 45 and how fast the temperature can penetrate into the surface. Of course, this is really strongly, it's a really strong function of the thermal inertia and the porosity. If we have a really high thermal inertia, temperature can penetrate deeper and maybe more ice can be lost. And of course, if we have more porosity, the resistance to loss is lower and more ice can be lost. But for me, as someone who did a PhD over the last 7 years, for me, the NPLD was always 5 million years. I remember even it was the Mars Polar Conference in Ushuaia, and there was a guy saying, maybe it's not 5 million years. And everybody said, no, this is 5 million years. This is a consensus. And for me now, if I need to put my money on, I'm not sure this is anymore 5 million years. Maybe it's 50 million years, and we just don't know what happened more than 20 million years because we don't know the orbital configuration.
Aaron?
Yes, I'm concluding. It's okay? I cannot let anyone on the... I'm not putting the next slide until I finish. So we developed a scheme in the Mars PCM to calculate the loss rate from subsurface ice. The ice loss shuts down completely at a certain depth. Of course, this is a function of the humidity and the lag layer properties. The migration of ice is complicated, and it's probably affecting both the physical and isotopic stratigraphy of the icy reservoirs. I didn't talk about isotopes today, but this is a subject close to my heart, and if anyone wants, I will be happy to discuss about it. And the future work, as JB mentioned, we really want to have the 3D simulation of high obliquity exclusion, and I finally want to know what's creating the lag layers and what size are the lag layers, and hopefully by the next conference it will be ready. Thank you.
Jacques Lascar, Paris Observatory. So that answers partially my question, my previous question, which was about what is the behavior at very high obliquity because of this period of high obliquity before 5 million years. And it's true that if you have a way to protect the ice, there is no more constraint, because the biggest constraint that we had in 2000 was that going to very high obliquity, then the idea is that the polar cap will not survive.
Yeah, we added many feedbacks that takes into account many stuff, like for instance, relaxation of vapor, how it's migrating from the pole. So if you sublimate a lot of ice and you have a lot of humidity, of course the ice is more stable, and in most models so far, they didn't have an atmosphere, and when you don't have an atmosphere, you can just continue to and more sublimate the ice.
Bruce Tchaikovsky. Aaron, I just want to agree completely with you about not knowing whether the polar caps appeared 5 million years ago. Certainly, if you start today and ran time backwards, you don't know what would happen at 5 million years. but since time runs forward most of the time, we don't really know what came before it, and we don't know whether the cap was there and protected, whether the cap was forming, whether it had disappeared entirely. Just an intractable problem right now.
Well, I agree with you partially. It's many people, some papers have not been accepted yet, but I know that they find more layers than what you find obliquity cycles in the last 5 million years. And you either need to find a mechanism that creates layers at different kind of something that is not orbital, or that you believe that it's more than 5 million years. So this is a hint saying maybe it's more than 5 million years. If you find, I don't know, 1,000 layers, either find the mechanism that creates them, or believe that it's obliquity, and then it has to be more than 5 million years.
As an example of a process that isn't obliquity related that could produce layers, global dust storms. We don't understand how, what controls the occurrence of global dust storms today, and there's evidence that the occurrence of dust storms varies dramatically on the decades to centuries timescale. So we have no reason other than intuition that may or may not be right to suggest that the layers we see are tied to obliquity.
Of course, this is true. There's plenty of mechanisms that can create layers, but so far we've seen a few dust lag layers, and they did not create a layer on top of the NPLD. So maybe yes and maybe no. Maybe there are other mechanisms. Maybe the dust storms were more extensive and this created a lag layer. But there's a lot of unknown, and we try to unfold it little by little. So if we have an high obliquity exclusion and we can understand where this ice is going and what is the size of the lag layer, maybe we can say something about this. And of course, the path is long until we find out what's the real solution.
Short question, short answer, please.
Excellent presentation.
All my answers are short.
Okay.
Jim Head, Brown University, excellent presentation. This is very important progress overall problem. I just want to say that in the 2003 latitude-dependent mantle paper, we did a mass balance and did not predict that anywhere near the total cap went away. Okay, that's for sure. And also,
of course, not the total cap. You just need a little bit to make.
Yeah, that's what we said. Of course. So I think also the latitude-dependent mantle is being eaten away at the lower latitudes, and we correlated some of that with the return of the ice to the polar region, and so that's another thing to look at.
Oh, this is perfect. I have a presentation about it this afternoon.
Thank you.
Thank you.
Thank you a lot, Aaron. Then we go to the last presentation before the lunch break. The first author of the abstract is Gabriela Gili, but she is not presenting. Francesco Gonzalez Galindo will present the work.
Hello everyone, I'm happy to present one of these interesting but long studies that Francois mentioned in his talk. In particular, this is a paper we recently published on the increased hadrian escape at the high obliquity conditions. And I'm presenting that on behalf of Gabriela Gili, who is the first author of that paper. How can I go back and forth? Okay, so atmospheric escape is one of the main suspects when invoked to explain the long-term evolution of water on Mars, and in particular to explain the fate of the water that was in Mars and the early and mid-Amazonian and is no longer there. So the mechanism to lose water operates through the atmospheric escape of its atomic constituents, hydrogen and oxygen atoms, and they both follow different pathways. So escaping hydrogen comes ultimately from water vapor photodissociation that followed by different chemical schemes, chemical reactions and transport processes, finish us with hydrogen atoms in the thermosphere. Hydrogen atoms are very light, so the atoms in the high energy tail of the velocity distribution have energy enough to escape from the planet. So it's important, this means that hydrogen escape is strongly linked to the water cycle in the lower atmosphere. For example, it has been observed that when there is a strong penetration of water into the mesosphere, something that happens regularly during the perihelion season but is boosted during dust events, this production of hydrogen atoms is significantly increased, and there is a quick and fast increase in the hydrogen escape as a reaction of this injection of water into the mesosphere. On the other hand, the escaping oxygen comes ultimately from the photoionization of CO2 that ends up in producing O2 plus ions, which are the dominant ions in the ionosphere. These O2 plus ions recombine with electrons and produce oxygen atoms, 2 oxygen atoms. This is a very exothermal reaction, so these atoms carry an excess of energy, and part of the oxygen atoms that are produced by this mechanism can escape from the atmosphere. So in principle, we have hydrogen escape comes from water vapor, oxygen escape that comes from CO2, so we could think that they are both separate things, but they are not, because there are chemical cycles linking on geological timescales of millions of years, linking the variation of CO2 with the variation of water vapor, in particular the products of water photolysis as a catalyst to recombine CO to produce CO2. And the net result for escape is that in the long term, in a steady state, if you want it, that has ever existed on Mars, there is a balance between there is a link between the number of hydrogen atoms that escape and the number of oxygen atoms that escape. In this work, we have focused only on hydrogen escape, but it will be important to keep in mind this balance between hydrogen and oxygen escape at the end. So the rate at which hydrogen atoms escape from current atmosphere has been inferred from measurements of the hydrogen corona by MAVEN and by Mass Express. Basically, this is one example. If you count how many atoms escape currently during a 1 Martian year, and you multiply that by the length of the Amazonian period, what you find is that current escape can only explain the loss of a couple of meters global equivalent layer of water during the whole Amazonian. This is significantly less than the assumed inventory of water that was on Mars in the early Amazonian. So what happens is that current Mars is not representative of the prevailing conditions during the Amazonian. In particular, the obliquity, the current value of the obliquity, 25 degrees, is significantly less than the most common value that is assumed to be 35 degrees. And you have been seeing all this morning on this conference that this has strong consequences of the climate of the planet, and in particular in the water cycle. So if we compare the current water cycle that we saw here to the left, as measured by Spican, for example, you see that the maximum column of water vapor is about 50 to 100 precipitated per micron. So in these experiments, this paper by Jean-Baptiste Madeleine, where he changed the obliquity to 35 degrees, he found that the amount of water in the atmosphere for high obliquity conditions can be more than 100 times larger than in the current orbital configuration. Of course, this is probably overestimated. We have seen that in the talk by François Forget, in the talk by Aaron Boss. So this is maybe not as intense as it is here, but we expect to have a more intense water cycle for high obliquity anyway. So the objective of this work was to use the Mars planetary climate model that we have been showing that can reproduce the current measurements of the measurements of current hydrogen escape to explore how would be the hydrogen escape in these high obliquity conditions in which the atmosphere was much more humid than it is today. For this, we use the Mars planetary climate model in its ground to exo-edge configuration, and including all the recent improvements into the water microphysics that has been described by Joseph Nahr before, but using this prescribed that distribution and the same distribution of ices in the planet, just focusing on the short-term effects on how the increase in the obliquity, the increase in the sublimation of the polar caps affects the water cycle. So what we do is we change the obliquity, and we then use the model, extend it only up to 80 kilometers, because it's much faster computationally, to compute, to evolve the water cycle until an equilibrium is reached, in the sense that we have a water cycle that repeats from one simulated year to the next one. Once we have this, that can take tens of simulated Martian years, Then we run the model again, including the upper atmosphere. We run 3 Martian years, and we calculate the hydrogen escape for the last of the simulated years. So let's go to the results. I will be showing different plots, showing the seasonal evolution of different magnitudes for 3 different simulations. Black is the simulation for current obliquity, yellow, the simulation for 30 degrees obliquity, red, the simulation for 35 degrees obliquity. We have tried to go to higher obliquities, but as Francois mentioned before, the model becomes unstable and we couldn't go farther than 35 degrees. So what we see here, if we look at the plot at the left, is that when going to current obliquity to 35 degrees obliquity, there is an important warming of the mesosphere. And this was something that was already found in this earlier paper by Jean-Baptiste Madeleine. The reason is that you have an increased sublimation, you have more water vapor in the atmosphere, and you start forming thick water ice clouds. And the radiative effects of these water ice clouds, basically these clouds, absorb infrared radiation and warm the mesosphere, the middle atmosphere. A warmer mesosphere means that the hygropause is much weaker, and then you can have much more water vapor penetrating to the middle atmosphere, as is shown in the middle panel. And as I mentioned before, more penetration of water to the mesosphere means that we have a significantly enhanced production of hydrogen atoms, so we have much more hydrogen atoms in the exobase. How does this translate into escaping hydrogen? So this plot summarizes the results. So basically, if you compare the black curve for current obliquity with the red one for 35 degrees, you see that there is an increase in the hydrogen escape that can go from 1 order of magnitude during the second half of the year to more than 2 orders of magnitude during the second half of the year. So what are the implications of this enhanced escape for the long-term evolution of water in the Amazonia? So I'm plotting here in these tables some numbers, comparing the 3 different simulations for the 3 different obliquity, and including here the average value of the hydrogen loss for every of the simulated Martian years, the minimum and maximum values of the hydrogen loss, and the annually integrated value. If we multiply this annually integrated value by, let's say, 4 billion years, what we find is that with the current obliquity, only about 4 meters of a global equivalent layer of water can escape, but if we go to an obliquity of 35, then up to 80 meters of a global equivalent layer of water can escape. And that's in better agreement with the estimation of how much water was there at the beginning of in the early Amazonia. However, well, within this, the fact that we have an increase in the hydrogen escape at high obliquity is kind of robust. The numbers should be taken with a lot of caution because there are many different processes. This is a very simplified study. There are many different processes that we are not taking into account. In particular, we are not taking into account this feedback between hydrogen and oxygen escape that I mentioned at the beginning, not because we don't have the chemical reactions in the model to operate that, but because this operates in millions of years of evolution, and we cannot run the GCM for such long times. Anyway, I have to mention that the fact that this operates in scales of millions of years, which is 1 or 2 orders of magnitude larger than the typical period of changes in the obliquity, cast doubts about whether this process would be an efficient restoring the hydrogen escape to lower values. We have not taken into account the changes in the ice distribution that Aaron Boss mentioned before, and that can produce a significantly less wet atmosphere for high obliquities. The plan would be to use the planetary evolution model framework to try to provide initial states from the GCM to try to check the influence of this process. We have not taken into account the fact that in high obliquity conditions, we may or may not have an increased dust loading in the atmosphere, and that will produce an immediate effect in the hydrogen escape. We have not taken into account the effects of the increased UV solar radiation, in particular at the beginning of the Amazonian, that both Shannon and Bruce presented in previous talks. And we have not taken into account the effects of potential modifications in the surface pressure. So, just to finish, we have our simulations, 3D simulation of hydrogen escape. shows that there is an increase in the hydrogen escape at high obliquity, at obliquity of 35, that produces an accumulated water escape in better agreement with the estimations of how much water there was at the early Amazonian. But this is a very first, I would say, crude approximation to a very complex problem. So there is a lot of work still to be done. So just keep tuned. I have put that there, the link to the paper, in case you want to get it. So thank you.
Hi, very cool work, thank you. Ranvos LMD. I was wondering, I know it's hard, can you distinguish between what part of the loss is due to increased humidity and what part is due to the warming? And maybe you can tell a little bit more about this.
Yeah, in fact, most of the important factor is how much water penetrates to the mesosphere. So no matter how much water you have in the lower atmosphere, I mean, no matter how the full column of water, what is important is how much of this water can penetrate to the mesosphere. And this is something that is driven by the temperature. A typical way of seeing that is that if you look at how the hydrogen escape rate varies in current conditions, you see that the maximum of the hydrogen escape happens in the second half of the year, where the atmosphere, in terms of column density of water, is less humid, if you want. And that's because the temperature in the mesosphere is higher in the second half of the year. So, yeah.
Really nice work, Francisco. I've struggled trying to understand the role of the first thing you listed on what you didn't include, and that's the feedback between oxygen and hydrogen escape. And my sense is that hydrogen escape is so rapid that the process ultimately is controlled by oxygen escape. So if you want to calculate the water loss, you really need to calculate the oxygen loss. Your thoughts on that?
Yeah, that's fair. Yeah, I agree with that. The thing is that, to calculate oxygen escape, it's a non-thermal process. That's something we cannot easily do with this kind of models. But yeah, so the idea was that this feedback mechanism tries to, when you have an increase of hydrogen escape, then you start accumulating O2, and that will reduce the amount of hydrogen in the atmosphere, reducing the escape. But that operates in very long time scale. That is efficient if you are able to get these conditions during a million of years of evolution. And my thought is that if you have variations of the obliquity which are 2 orders of magnitude faster than this time scale that you need to stabilize the hydrogen escape, maybe that's not a very efficient mechanism. So maybe finally these variations in hydrogen escape are faster that can be stabilized by this feedback with atomic oxygen escape.
Unclear. If you look at the present seasonal cycle, you see an order of magnitude seasonal variation in the hydrogen escape rate. You showed that. And you see absolutely no significant variation in the oxygen escape rate, yet we still think they're coupled. And I think you ultimately have to look at how things work on all the different timescales, from daily, which is how escape of an individual atom occurs, all the way up to the 10 million, tens of millions of years.
Yeah, fully agree, but that's difficult study. But yeah.
Thank you, Francesco. Thanks again to all the speakers of this session. We reconvene after lunch at 2. We start, right? Okay, great. Thanks, everyone.